Hello wonderful person, this is Anton, and you're looking at a typical ring galaxy. This one is actually very well known. This is known as the Hughes object. But even today, we still don't really know how these objects came to be. Their origin is a bit of a mystery. But wait, don't leave yet, because we're not really talking about ring galaxies. We're talking about wormholes, because at least one paper out there proposes that these galaxies were probably created through the formation of different wormholes across the universe. So yeah, we're going to be talking about a very theoretical but also somewhat intriguing paper. The paper that, as always, you can find in the description below, and the paper that I discovered while doing research on the newly discovered mysterious objects known as odd radio circles. And so let's discuss this in a little bit more detail, because even though it is theoretical, it still is interesting and could actually make sense. And let's start with the theory. The theory behind wormholes is pretty solid. Theoretically and mathematically, we do believe that they can exist and possibly do exist. And all of the theoretical explanations about wormholes starts with the Einstein's predictions in regards to space-time itself, with wormholes being a kind of a shortcut or a connection between two different points of space-time. Now, in his theories, he predicted the idea behind black holes and the idea behind white holes. And although we've confirmed one of his ideas, the black holes, the white holes have never really been found, and nothing we've seen in the universe so far has in any way resembled any of the predictions of what white holes should look like. Nevertheless, we still understand that space-time can be stretched, it can also be bent, it can be twisted, and it can technically connect two different points. For example, this image right here shows you the famous prediction from 1935 of what Einstein and another physicist by the name of Nathan Rosen proposed could be possible between two different sheets of space-time. They could hypothetically connect to one another and create a kind of a hole in between. This is also sometimes referred to as the Einstein-Rosen bridge. And here, a typical wormhole would contain two different mouths and one throat. You kind of hypothetically go through the throat to get from one mouth to the other. The mouth itself, just like in Interstellar, would not really be a hole, but a 3D sphere. The sphere would be the hole, because you know, in 3 dimensions, a hole is actually a sphere. Once you go through one sphere, you come out on the other side. But the natural question here is, of course, can we go through a wormhole, and obviously do they exist, and do things go through them to begin with? And this is kind of where we come to the point where the mathematics and the physics don't really agree with what we want to believe and with the science fiction we get to see in the movies. So for example, mathematically or in terms of physics, in order for a wormhole to stay open, it needs to somehow prevent the gravity from shutting the wormhole down. Now, theoretically, we believe that wormholes may have actually existed in the early universe, especially as the universe started to expand very suddenly. But it's also possible that all of these mouths, all of these wormholes, have actually been closed a long time ago by the forces of gravity. In other words, something has to act on the actual throat of the wormhole in order to prevent it from shutting down and from essentially closing permanently. But is there anything that can keep the wormhole from closing down and from shutting down permanently? Well, in theory, mathematically speaking, negative energy is one such thing that can try to resist gravity from shutting down the wormhole. In other words, certain types of exotic energy and exotic matter could hypothetically prevent a wormhole from shutting down. But a lot of this exotic stuff only exists on paper. Most of it has never been produced. And the idea of negative energy, well, it theoretically is possible. As a matter of fact, one type of negative energy is what we believe dark energy is. So that strange energy that exists in a universe that seems to cause it to expand faster and faster is one type of negative energy. We kind of think we understand it, at least mathematically, but we obviously have no idea if it can actually go inside a wormhole and prevent it from shutting down. Theoretically, obviously it's possible. As a matter of fact, theoretically it's possible that the universe has been doing this for billions of years. We just don't really have any physical proof of any of this. In other words, we don't really know if this negative energy can indeed prevent a wormhole from shutting down. But we do know that if they do exist, there should be ways for us to detect the effects around this wormhole and thus prove its existence that way. Now, interestingly, if you were to go on Archive or really any other scientific website and look up wormholes, you'll find thousands of scientific studies on the topic. As a matter of fact, it seems like every week there's a new study either describing what a wormhole could be or how we can find them, or even studies trying to prove that we've already detected them, just never really realized that we're looking at a wormhole. For example, there are several studies that suggest that the object in the middle of our own galaxy, the object known as Sagittarius A star, could hypothetically be a wormhole, and there are actually very specific ways we can establish if it's a wormhole or a black hole. But at the moment we can't really discover which one it is yet, because a wormhole would have slightly different gravitational effects on the nearby stars. So by watching these stars that you can see right here for much longer periods, we'll actually be able to establish which one it is. Is it a black hole or a wormhole? For now, most people agree that it's most likely a massive black hole. Nevertheless, because mathematically and physically it can totally exist, for many years now, various scientists have been trying to discover any kind of a proof for the existence of these unusual and somewhat mysterious but also super exciting objects. And although mathematically they're definitely possible, and physically they can definitely exist, it seems that discovering them has been extremely challenging, and also trying to maintain their existence, even in theory, is also not very easy. Which I guess takes us to this new paper from the Russian scientists that suggests that, well, maybe, just maybe, the wormholes are actually created in the middle of these unusual galaxies known as ring galaxies. And also maybe, just maybe, we've also seen the signs of these wormholes, or at least the interaction of these wormholes, very recently. Which in some sense actually connects two different mysteries and tries to resolve both of them at the same time. So, as I mentioned before, ring galaxies, like the Hubble object here, don't really have a very clear origin. We know they exist, we know they're absolutely beautiful, and we know there's a lot of them out there. And some of them have really unusual and really difficult to explain shapes, yet others, like the famous Hubble object, seem to even have a ring galaxy inside of them, although technically this other smaller galaxy is not just inside, it's much farther away, simply because of the redshift that it's exhibiting. But these unusual galaxies still don't really have a very good explanation for how they were formed. And they also seem to exhibit certain properties that are still not very well explained either. And when we find something mysterious in the universe, there are going to be naturally a lot of interesting explanations. One such explanation is that maybe, just maybe, these ring galaxies formed around a very massive wormhole that either existed in the past or even still exists there today. And the scientists in this paper explain that essentially by having a wormhole and certain effects of this wormhole right at the center, it would then force the matter around itself to form in such a way that it would actually form a ring. What's more is that they also suggest that sometimes when this matter falls into this wormhole, it's obviously going to collide with some of the other matter on the other side, as it's probably falling into the second mouth on the other side. But the thing is, at some point, some of this matter will collide and produce a tremendous amount of gamma rays and a lot of other radiation, which will seem like it's emanating from the center of this particular galaxy, or from essentially the center of the wormhole. Now, we know that black holes can definitely produce gamma rays, but we also know that for a typical black hole, the energy released is going to be in a kind of a point form. It's going to be these two jets emanating from both directions. And that's because of the way that the black hole and the accretion disk essentially entangle everything using the magnetic lines and cause them to be released in two different directions. But unlike a typical supermassive black hole, a wormhole is not going to produce jets, but is instead going to produce a sphere of gamma ray emissions, or a sphere of very powerful emissions of some other sort. So in other words, it's going to look sort of like a spherical bubble, a bubble around a relatively massive object in the middle. Now, this is one of the explanations for how these rings were formed, but what's more interesting is that this is how the scientists in this paper also explain the mysterious odd radio circles, also known as ORCs, that were only discovered less than a year ago from when I'm making this video. You can learn about them in one of the videos somewhere right there. And so the scientists here are trying to basically solve the mystery of why ORCs exist, and essentially explain it as the emissions from these wormholes that probably exist in the center, but also explain how the ring galaxies formed as well. And furthermore, they also explain that a lot of these ring galaxies only formed because of the wormholes in the middle. Basically here, the wormhole, or the actual mouth of the wormhole, provides the gravitational foundation for the formation of everything else in this galaxy. And because of this, the scientists also mentioned that they don't think that there's going to be a very large dark matter halo here. In other words, the matter here is going to be mostly visible, there's going to be practically no dark matter. And all of these propositions, at least at the moment and at least mathematically, are not really that far-fetched. There's obviously no physical proof of any of this just yet, and there are obviously other explanations that can be used to maybe explain all of this, but it's still a proposition that's worth investigating. Especially since wormholes and white holes are actually a predicted phenomenon in Einstein's theories, and black holes have already been proven and even found to exist physically. But there is, however, an important side note here. It does not mean that if these wormholes exist, we can start traveling across them. Because mathematically and theoretically, any regular matter passing through a wormhole can actually completely shut it down, destabilizing everything in between and basically making it not exist anymore. So theoretically at least, there's probably still no way for us humans and our spaceships to travel through these wormholes and to go from one location to another. But despite all of this, it's still really important for us to study these objects even in theory. And there's one really important reason for this. Today the physicists have been trying to figure out the so-called theory of everything. The theory that can connect all of the different physics in basically one single topic. More importantly, they've been trying to find a way to connect the quantum mechanics to the theories of Einstein and the theories of gravity. So far, no such theory exists, but we know that the idea of wormholes to some extent connects to the idea of quantum teleportation that has already been achieved in the lab. Which means that there is a way for us to theoretically connect quantum mechanics and quantum teleportation to the gravitational theories related to wormholes and space-time travel. And most of this is because the quantum teleportation that has been achieved in the lab works in a very similar way to how mathematically we think a typical wormhole would transfer information as well. And so in that sense, by studying wormholes and by studying the effects of gravity in the wormholes, and obviously by trying to find them somewhere out there and possibly even finding one somewhere out there, we might one day be able to create this theory of everything and finally understand how the universe works. For now though, it's definitely a very interesting proposition, and it's also a pretty interesting idea to begin with. If the ideas that these scientists propose have any merit, it means that we can actually solve a lot of mysteries with a single explanation. But for now we definitely need more studies, we need more investigations, and we obviously need a lot more observations of various galaxies and various unusual phenomena out there. Hello wonderful person, this is Anton, and imagine for a second you're looking at the universe, you're looking at the night skies and you're trying to discover something new out there. You're using a radio telescope for that, and as you're looking around you discover something we have never seen before. Something that's so unusual and so strange that you don't even know what to name it. And you end up naming it ORC, which stands for Odd Radio Circle, because it's only seen in radio waves, it's circular, and it's super strange. So this is exactly what the scientists just recently discovered, and they found 4 of them in the night skies. So before I start, we know absolutely nothing about these objects. 4 of them were discovered in the night skies, 4 of them seem to be somewhat similar, and 4 of them are absolute mystery to us right now. We don't really know what formed them, we don't really know how far away they are, how big they are, and what exactly they are to begin with. But we do know some things. And first of all, what exactly and how exactly was this found? Well, first of all of this was done in radio frequencies with radio telescopes. A lot of these are usually in Australia because the night skies there are extremely beautiful, very quiet, and there's practically no one for hundreds and hundreds of kilometers in every direction, so normally you can see absolutely everything in the night skies. And very recently this new project known as EMU, or Evolutionary Map of the Universe, was started by one of the Australian universities to try to create a much more detailed radio map of the night skies of the universe itself. Currently all of the maps of the universe only have approximately 2.5 million different radio objects in them, and this was done a few years ago, so our actual radio map of the universe is not really that good just yet compared to some of the other maps. And especially with discoveries of new radio phenomena like, for example, FRB, fast radio bursts, and some of the other unusual phenomena I covered in the video of the Exotica catalog from SETI, I've talked about some of the mysteries that we already have with the currently observed radio telescopes. But the EMU program expects to discover at least 70 million more different objects. essentially creating a map that's about 50 times higher in resolution. And it didn't really take long for the scientists to discover something unusual already. And that something is actually pretty big. It's not something small. So it's very surprising that we didn't really see it before in some of the previous surveys. So as I mentioned, these objects currently have no explanation. We're just going to call them ORCs, odd radio circles. Only 4 of these objects were discovered so far, and all 4 of them are, well, they're circles. They seem to be pretty big in the night skies, but we obviously don't really know how big they are because we don't really know how far away they are. In terms of the actual size, if you were to compare them to, for example, a full moon in the night skies, these are about 30 times smaller. So they're not really that big, but they're also not really small. They're technically bigger than a typical star would appear if you could see them in radio waves. But we probably didn't see them before because they are kind of faint. They're somewhat difficult to see. They also seem to have slightly more brightness on the edges as compared to the rest of the circle. But except for these observations right now, we have no idea what's going on here. We actually have no physical interpretation to this. We don't really know if these were results of some kind of a powerful explosion. And because we've never really observed these from other known phenomena like, for example, supernova, which do often leave circular objects, we know that it's most likely not related to a supernova because none of them ever produced something similar in terms of the shape and in terms of the actual frequencies. And what's most important here is that even though these objects are visible in radio waves and are quite large in terms of the size in the radio waves, if you were to look at them in any other frequency, including microwave, infrared, visual light, or any other light, so even ultraviolet, X-ray, and gamma ray light, you would see absolutely nothing. So they appear to be only visible in radio waves, and because of their sheer size and also because there are 4 of them there, this actually creates a very interesting and very peculiar phenomenon. So something happened there, but it's only visible in radio waves. Now, because we don't really know how far away these circles are, we also don't know if they're connected to anything. Like, they might be actually connected to certain galaxies, and these could be produced by very powerful emissions from a galaxy, but only 2 of these objects seem to have a galaxy nearby, or actually in their center. 2 other objects don't have any galaxies there, or maybe they are there, but they're just really far away and invisible to us. So for example, here in the so-called ORC2, these 2 objects are lobes of a radio galaxy far away. But we're not entirely sure if these objects are actually connected or if the ORC object is much closer or possibly even much farther away. So right now there's just not enough information to suggest that these objects are in the same plane and are at the same distance. And although it's possible that maybe these are just radio galaxies seen from a different perspective or something else related to radio galaxies, which usually create some of the biggest and brightest objects in radio waves compared to what you would see in visible light, there's still just not enough information and not enough data to suggest any of this. Also, because this is the first time we actually see these phenomena and we've seen a lot of radio galaxies before, it's kind of unlikely that they're related. Or at least maybe this is just a completely new phenomenon from the radio galaxies we've never really considered before. And although they do kind of resemble this, for example, this is actually what a typical star-forming galaxy, a radio galaxy in this case, looks like in radio waves. It's basically a circle with the edges quite visible. This was actually from a galaxy known as NGC 6935 that you see right here in visual light. There are still way too many differences here in terms of the shape and even the frequencies emitted. But in the paper, the scientists go through all of the potential explanations in a lot of detail. Like, for example, supernova, which they think it's not, strange planetary nebula, which they also think it's not, a star-forming galaxy or some sort of a radio galaxy, which once again they think it's not, or any of the other unusual phenomena, including the well-known Einstein ring, which is usually formed by the gravitational lensing effects, and in this case we usually see them in visual light, but they obviously could also form in radio waves, and this also seems to be not the case. So using many different potential physical explanations, at least using common physical phenomena, the scientists sort of come to a conclusion that none of them are satisfactory. It's not an unusual star, it's not an unusual galaxy or a nebula, and it's not an unusual gravitational physical phenomena. It's probably something completely new, something we've never seen before, and something we haven't really considered just yet. And this is actually somewhat similar to how we originally discovered the mysterious FRBs. Today we kind of are getting closer to explaining them, but back then they made absolutely no sense. So it's quite possible that this is possibly a completely new phenomenon, something that scientists will now have to try to figure out. And since we've only found 4 so far, we definitely need to find more of these objects to try to make sense of them, to try to understand what formed them, how far away they are, and also how big these objects actually are. Because right now they could be either as small as a typical star system or as big as some of the largest structures in the universe. Hello wonderful person, this is Anton, and this right here is a galaxy known as Messier 49, the brightest galaxy in the Virgo cluster, the largest galactic cluster next to us, located around 55 million light years away from us. And it contains a lot of galaxies on the inside, thousands of them as you can see from this image. Many of them are very similar to the Milky Way, but a lot of them are also extremely different. They're kind of similar to Messier 49, and the most famous galaxy here is the one we've discussed many times on the channel. It's the galaxy known as Messier 87, or M87 for short, the galaxy that also became famous for the iconic image of its black hole right in the middle, the M87 black hole that we've discussed on the channel many times. With the galaxy and the black hole located right in the middle of this particular cluster that we're discussing because of a recent study that was able to analyze it using some of the new techniques. And also producing some of the images that we've never really seen before. This is what this cluster looks like with a new survey known as Vertigo, which stands for Virgo Environment Traced in Carbon Monoxide. The new survey that revealed the galaxy in radio light mixed with X-rays and that essentially tried to answer a relatively simple but somewhat difficult to answer question. What's killing all of the galaxies in a lot of different galactic clusters, including the Virgo cluster? Which is essentially one of the questions we're going to try to answer today, while also exploring the Virgo cluster itself. And all of this, as always, you can find in the description below, including the survey that focused on carbon monoxide and tried to reveal the activity of various galaxies and various galactic interactions, essentially answer the question of what's really killing these galaxies. But I guess to start, what do we mean by killing the galaxies? What does life have anything to do with this? Well, generally speaking, when it comes to galaxies, when we say a living galaxy, it means the galaxy that's still producing stars. Or essentially a galaxy that uses a lot of cold hydrogen gas to sort of clump into bigger chunks and to then have stars somewhere in the vicinity. With some galaxies being really good at this, producing hundreds and hundreds masses of the sun per year, and some other galaxies being almost completely quiet for one reason or another. Now, sometimes it's because of an extremely powerful black hole in the middle that tends to produce very powerful winds, but in other cases, the reasons are not entirely understood. And some of these observations from various galactic clusters do suggest that many galaxies inside these very massive clusters tend to eventually stop producing stars. In other words, they kind of become dead. But what exactly kills them is the question the scientists have been trying to answer for a pretty long time. And the thing is, in the past when the scientists were looking at various galactic clusters, especially the really famous ones with a lot of mass on the inside, this one here you can see produces a lot of different gravitational lensing effects, they've realized that many of these clusters contain a lot of these really old and very red galaxies that generally just have a lot of ancient stars, but absolutely no star production on the inside. As a matter of fact, most of these so-called dead galaxies seem to be inside large clusters. They're very unlikely to be alone by themselves, and many galaxies that tend to still produce stars, like for example the Milky Way galaxy, will usually not really be in the middle of a large cluster. It will be in some sort of a small neighborhood, like the one we refer to as the local group. Here's by the way what the local group sort of looks like, with the center right there being the Milky Way, with a few neighbors that we have, smaller dwarf galaxies. But as you can see, generally speaking, it's actually a relatively empty neighborhood. We have the Andromeda Galaxy and the Triangular Galaxy and a few dwarf galaxies here and there, but compared to a lot of other neighborhoods, this is actually relatively empty. But Virgo cluster, located around 55 million light years away from us, is an extremely interesting opportunity for us to study all of this. First of all, it's obviously the nearest massive cluster. It's actually so massive that it produces gravitational pulling effect on the entire local group, reducing the overall velocity of all of the galaxies here by roughly around 10%. This is referred to as the Virgocentric flow. But more importantly, apart from the distance and from the mass, and also unlike other clusters that scientists have studied for many years, the Virgo cluster seems to be really unusual in that it's a mixture of different types of galaxies. And you can sort of see this in this image taken by the Hubble telescope a long time ago. It's a mixture of different spiral galaxies, such as the Milky Way galaxy, which is already unusual because a lot of clusters normally tend to disrupt their structure, but also a lot of these elliptical galaxies with extremely ancient stars and barely any star production, if any at all. And once again, there are nearly 2,000 different galaxies here, at least the ones we can see. There are probably a lot of invisible dwarf galaxies on top of that. We only have 3 galaxies in the local group. And it's also generally believed to contain 3 different subgroups, with each of these subgroups slowly joining, which will eventually turn this into one large cluster. And a lot of these signs suggest that this is a relatively young cluster. It's a cluster that's still forming, and it's a cluster that basically hasn't really killed all of its galaxies just yet. Which means that it's a perfect opportunity to try to understand what's going on here. But interestingly, this cluster is so massive that some of the galaxies here move at ridiculously fast speeds, nearly 1600 kilometers per second, or about 1000 miles per second. And so some galaxies zoom past each other really fast. But in order to understand what happens to these galaxies long term and what stops their star production, we also have to look at what happens between the galaxies and try to analyze a lot of the activity in the intergalactic space. Or in this case, it would be referred to as the ICM, intercluster medium. And today the scientists believe that ICM is basically just a lot of super hot gas. It's essentially plasma, with temperatures reaching 30 million Kelvin. That's way hotter than the surface of the sun. And basically because of this, this produces a lot of X-rays. X-rays that can be visible from very far away distances. That's also sort of visible in this image as these tiny blue spots all over the place, including a relatively large one right here, that's the M87 galaxy. But surprisingly, or I guess maybe not surprisingly, the ICM, or the intercluster medium, also contains a lot of other stuff. I guess in some sense you would call it leftovers from various galaxies. As a matter of fact, up to about 10% of all of the stars from all of the galaxies in the cluster are in the ICM. They're outside of galaxies. They were most likely kicked out for one reason or another when various galaxies were colliding. ICM also contains relatively large clusters of stars, including globular clusters, and there's even at least one detectable region that produces its own stars outside of the galaxy. Basically, there is a very large hydrogen cloud with a relatively massive star production, but outside of major galaxies. This was originally discovered approximately 20 years ago. And so this recent study that conducted the largest high-resolution survey of the galaxies, investigating various star-forming regions in these galaxies, decided to specifically focus on 51 galaxies inside the cluster in order to reveal the extreme environments that they currently have on the inside, essentially discovering the phenomenon that we refer to as the galaxy quenching. And galaxy quenching or galactic quenching can occur for various reasons. It can be because of extremely powerful winds from the black hole in the middle. It can also be because the galaxy just runs out of gas completely because all of the stars have already been created. But in this case, it really seems to occur because of the extreme effects inside the cluster. Extreme speeds, extremely high temperatures and gas, and just huge amounts of this super hot plasma with millions of degrees in temperature that interacts with various galaxies in such a way that it basically strips those galaxies of any cold gas on the inside. Or in other words, as a lot of these galaxies move around with speeds of thousands of kilometers per second, they end up hitting the super hot gas at very high velocities, which then strips them of any cold gas, cold hydrogen gas, and prevents them from forming stars in the future. And this is a really interesting phenomenon referred to as the gas stripping. The gas is literally stripped from the galaxies. All of which happens simply because the galaxies are moving way too fast, the gas is way too hot, and the collisions become extremely energetic. And eventually all of these galaxies are most likely going to end up just like M87, M49, and a lot of other elliptical galaxies, filled with ancient stars and absolutely no star production whatsoever. But that's in the next few billions of years. For now, they still have stars, they still have production of stars, and they're still doing fine. Maybe some of those galaxies might even get completely kicked out of the system and might survive even longer. Although unfortunately, all of this is basically billions and billions of years in the future, so chances are we're not really going to know what's going to happen to them ever. Nevertheless, it's a pretty exciting study and gave me a really good opportunity to talk about this incredible cluster. And by the way, in case you were wondering where exactly it's located compared to sort of the Andromeda Galaxy compared to the Milky Way, well, this map right here can sort of help you visualize some of this. If this is the local group, and specifically right here, this is where the Milky Way galaxy is, by going approximately 55 million light years toward this location, you're going to discover the Virgo cluster. And this here is this large and extremely massive component that represents just a part of the supercluster that also happens to have the name Virgo. And altogether, all of these galaxies are actually moving in a certain direction, a direction that we sometimes refer to as the Great Attractor. But we'll talk more about this in some of the future videos, so make sure to subscribe. Anyway, on that note, well, pretty interesting discovery, a great opportunity to talk about the Virgo cluster, and more importantly, incredible new images that will allow scientists to study this cluster and discover some more hidden details somewhere within. Hello wonderful person, this is Anton, and today we're going to be talking about yet another unusual mystery discovered in regards to nearby dwarf galaxies, or more specifically about dwarf galaxies surprisingly reacting to and also somehow being affected by various things coming from the central galaxy, or possibly from something entirely different, possibly from the mysterious cosmic web. Either way though, the discoveries are coming from two different studies and currently do not have a very good explanation. So first of all, let's begin with this study right here that as always you can find in the description below. In this particular study, the scientists decided to analyze some of the nearby dwarf galaxies, taking a look at what happened to all of them in the last 6 billion years or so. Now you might be already aware that various large galaxies such as the Andromeda that you see right here or the Milky Way that's right here all possess a lot of different dwarf galaxies in their orbit. The most famous dwarf galaxy in orbit of the Milky Way, or technically it's actually a pair, is the galaxy you see right there, that's the Large Magellanic Cloud, but also its partner Small Magellanic Cloud that also orbits around the Milky Way as well. More than 20 different dwarf galaxies are known around the Milky Way, with even more around the Andromeda Galaxy, with a lot more probably still hiding and just being too dim to detect. But for this particular study, the scientists looked even beyond that, all the way to about 13 million light years away from the Milky Way galaxy. And here is sort of what the map of all of this looks like, with some of the galaxies being visible in this particular picture. And it's important to understand that all of these galaxies are really far away from each other, with most of them being at least 1 million light years away from one another. But strangely enough, what the scientists discovered is that all of these galaxies, all 36 of them, experienced a somewhat simultaneous and accelerated birth of stars, which was then also followed by a somewhat simultaneous shutdown of star production as well. Which kind of doesn't make sense because it's as if all of them were influenced by a single event, as if they were all somehow connected. And remember, once again, some of them are about 13 million light years away from one another. That's about 6 times the distance of Milky Way to Andromeda. They're also located in somewhat diverse environments and have somewhat diverse partners. And so it's really unclear how is it that all of them experience similar events around the same time. And so on the one hand, maybe it's a new phenomenon that nobody understands and nobody really knows what's happening here. But on the other hand, there's also this unusual discovery around the same time as well. And this one is in regards to the analysis of close to about 130,000 different satellites or dwarf galaxies in various galactic systems out there. And for this study, the scientists did take a look at many different galaxies out there. And to their surprise, what they discovered is that, for the most part, the central galaxy seems to actually influence the dwarf galaxies quite a lot, but not in the way they expected. The observations from their study suggest that depending on the orientation of the dwarf galaxy around the central galaxy, it's going to be going through various stages of star formation. Or more specifically, there are certain regions around the central galaxy where a typical dwarf galaxy is going to go through what's known as the quenching event. It's essentially when the star formation suddenly shuts down and no new stars are being formed. And when it comes to quenching, it's generally understood to be caused by the central black hole. So in this particular case, when the central black hole suddenly starts to produce a lot of energy, while also starts releasing a lot of cosmic wind and produces these very powerful astrophysical jets, this has a tendency to shut down any star production in that particular galaxy. But this power can sort of extend to nearby galaxies as well. At least that's what the scientists believe theoretically. Now, so far the observations from active galaxies more or less prove this idea. Essentially, the star formation does shut down when the galactic center becomes extremely active. This is what's referred to as the active galactic nucleus. But what about these dwarf galaxies orbiting around the active galactic nucleus galaxy? Well, in that case, the assumption would be that maybe if the dwarf galaxy passes somewhere in the region where the jets are essentially bombarding it, maybe this is how the dwarf galaxies are quenched as well. Or to sort of help you visualize this, if a dwarf galaxy passes right here at the 90-degree angle, or on this side of the central galaxy, it's possible that in those particular points, the dwarf galaxies will experience quenching and will stop producing stars as well. While naturally the 0-degree angle, or I guess the 180-degree angle right here, would maybe represent the best position for dwarf galaxies to produce stars. To test all of this, the scientists used the famous Sloan Digital Sky Survey, which allowed them to study thousands of different galactic groups and galactic clusters, while at the same time using the famous Illustris project simulation to try to simulate this on a computer as well. Well, they discovered something, but it wasn't what they thought they were going to discover. The simulations and the analysis showed that quenching indeed happens in certain parts around the galaxy, around the central galaxy, but it happens in almost the opposite regions of where they assumed it would happen. Even though there's a lot of energy coming out on these two sides, and the central black hole here produces a tremendous amount of power, it was really the regions around the major axis right here that were responsible for the most quenching in these dwarf galaxies, with more star creation and star formation happening in the regions that to some extent were bombarded by the astrophysical jets from the central black hole. With this graph right here sort of showing us how all of this changes as the dwarf galaxy orbits around the central galaxy. And this of course implies that the central black hole and the activity of the central galaxy directly influences the dwarf galaxies around it. But what exactly happens here, and why is it that it's the opposite of what it was assumed to be? Wouldn't these astrophysical jets sweep the entire area of any material, preventing star formation? Well, I guess one of the possible answers here is that it seems to be doing the opposite. It seems to be actually directing some of the gas into those galaxies, providing some of the material for star formation. Or at the least, it seems to cause various molecular clouds in those galaxies to start colliding and to start producing more stars. Now naturally it's still kind of not known what exactly happens there, but that's one of the possible explanations. On the other hand, the regions to the side of the central galaxy, or essentially at the major axis of the galaxy, end up creating regions of really low density. And this in effect might actually cause some of the molecular clouds from within these dwarf galaxies to start sort of moving on the outskirts and thus reduce the star production. Or basically it produces kind of like more vacuum than actual vacuum. It produces lower pressure. And as a result of this lower pressure, a lot of the star building material starts to slowly move out, with once again the central black hole here being responsible for all of this activity. And this is once again an important evidence for the importance of these central black holes in sort of helping the galaxies and of course the universe itself to evolve in a certain way. A lot of different computer simulations that involve creation of galaxies and central black holes often show us how the black holes here really guide everything. They guide the production of satellites, they guide the production of stars and of course various types of matter around the galaxy, but they also seem to guide the production of stars in nearby dwarf galaxies as well. And so these central black holes in various different galaxies do play an important role in the evolution of the universe. But it still doesn't really answer the important question of what happened to those 36 galaxies I mentioned in the beginning. Now obviously it could be because of the activity of various central black holes in, for example, Andromeda Galaxy or the Milky Way Galaxy. But it could be something entirely different, which also means that maybe these galaxies that I've discussed just now also have been influenced by something else as well. One potential culprit and one potential explanation is the mysterious cosmic web. We've already discovered that it does so many things that we didn't know it does. For example, it seems to be spinning and providing a lot of angular momentum. It also seems to be guiding a lot of matter everywhere. And for all we know, it might also act as a kind of a switch for all of the nearby galaxies. But that's of course a very preliminary assumption. Nobody really knows what really happened until we find something else out there that helps us with observational proof of what really happened in those galaxies. Our night skies change all the time. Some stars become brighter, some stars become dimmer, and some stars slowly move across the night skies. But by looking at the night skies long enough, we can also start discovering some other mysteries. One such mystery is what the scientists refer to as vanishing stars. Stars that kind of just disappear. Hello wonderful person, this is Anton, and today we're going to reflect back on this idea of vanishing stars that I first mentioned approximately 2 years ago, because since then, the researchers behind this particular study have also discovered a lot more of these unusual vanishing stars. Stars that, for one reason or another, seem to have completely disappeared in the last few decades. And although initially the scientists discovered only 100 of these stars, with the help of the citizen science project known as the VASCO network, the network that you can learn more about from this paper right here and that you can also join yourself, they now have identified approximately 800 of these unusual objects, or technically they're not there anymore, so I guess missing objects, with many such disappearances currently not having any good explanation at all. It's as if something either covered the star, or if it just shut down its activity and became something entirely different. And so in this video we're going to discuss some of the potential explanations, and I'm also going to show you where you can join this citizen project yourself if you want to participate in it as well. The project that several scientists discussed during this SETI talk right here, mostly because this also represents one of the most exciting projects in regards to the search for extraterrestrial intelligence. Naturally, because one of the potential explanations here is that this could be some sort of a megastructure just hiding the star itself. But that's of course not the only and not even the best explanation so far. The best explanations are still natural explanations. So what exactly is going on here? Well, naturally we know that stars can disappear for many different reasons. For example, a supernova. But during a typical supernova you would also expect a lot of other emissions, but also possibly some sort of a leftover, some sort of a nebular cloud that should be detectable afterwards. Yet as of now, as of today, none of these objects investigated in the study here had anything left behind. There was no extra emissions, there was no additional radiation, it's as if the objects just sort of vanished. Okay, well, what can possibly do this? So let's start right here. Where do these pictures actually come from? Well, the original pictures, the original images, were taken by the US Navy, the United States Naval Observatory to be more exact, and this was done several decades ago, back in the late 40s, in the early 50s. In case you were not aware, the US Navy uses what's known as astrometry for extremely precise navigation reasons, and so US Navy has some of the most advanced capabilities when it comes to observing the stars and taking various pictures of various objects. And so over the years they've taken a lot of pictures of various stars. But a few decades later, several other surveys started to take more pictures, with one such observatory being Pan-STARRS. Now these are obviously not done for military reasons, this was mostly done for research reasons. And you can actually even access all of this data yourself because all of this is publicly available. And so the scientists behind this study wanted to figure out, well, has our night skies changed dramatically? They wanted to see if any of the objects possibly appeared or disappeared. And this could be obviously for many different reasons and could be explained in a lot of different natural ways. But to their surprise, it didn't take them long to start discovering a lot of these vanishing objects. Stars or some bright objects that were there in the 50s but were not there in 2000s, approximately 5 decades later, with the total number of observed and detected objects increasing more and more as more people joined their project and helped them discover even more of these vanishing stars. Although, okay, let's do a bit of a correction here. I call them stars, but it's not necessarily stars at all. We don't actually know what was seen by the Navy back in the 50s. Obviously they could be stars, but they could also have been various types of transients, various types of bright, sudden events that only stay bright for some time, possibly a year or 2 years, and then disappear completely. Now, this could be obviously some sort of a supernova, but a more likely explanation here would be just a regular nova. essentially a thermonuclear reaction on the surface of some sort of white dwarf. Now these happen all the time and we actually detect them pretty much on a weekly basis. And these do produce very bright emissions that could have actually been captured back in the 50s and would not be present right now. But the problem here is the number of these objects discovered so far. It's very unlikely that several hundred of these objects would be visible in the 50s and not visible today. So nova by itself does not explain the origin of all of these objects. Maybe some of them, but definitely not all of them. Now one way to prove if this is a nova is to actually possibly see these objects again. A lot of nova happen many times. Many of them are recurrent nova, so if suddenly one of these objects reappears again, we'll know for a fact that this is exactly what happened here. At the same time, maybe this is just some sort of a really bright flare, for example from an extremely active red dwarf. We know that many red dwarfs, including the nearby Proxima Centauri, are actually very active. They produce tons and tons of flares that temporarily increase their brightness. And so this could be a potential explanation for some of these vanishing objects. It's not that they vanished, it's just at that particular time in the 50s, they were much brighter than usual. But once again, the numbers here don't really add up. The recent analysis identified over 800 of these objects already, and having 800 flares happening at the same time does not explain all of these objects. The other intriguing explanation here involves what's known as the collapsar, essentially when a somewhat massive red supergiant sort of skips the supernova part and collapses into the black hole directly, which would cause the star to disappear completely. For example, one such collapsar was detected in one of the galaxies nearby, but normally there are at least some leftovers that we can hypothetically detect from these particular systems. It could either be the emissions from the previous interaction with the gas in the star system, or some other unusual signs that should still be detected even after 50, 60, 70 years. And so one potential explanation here would be to double check these areas to see what other emissions we can detect. So far this has not been done because the scientists only started doing this not so long ago. At the same time, this could be some sort of a variable star. But the fact that variable stars generally return back to original brightness means that we should be able to see these stars again. At the moment, none of them seem to be visible. Also, for a star to completely disappear, it would have to be some really extreme version of a variable star. So this, right now, is the least likely explanation. Okay, how about some other unusual events, other transients? Here, the scientists speculate that maybe fast radio bursts or gamma ray bursts could be responsible for producing some of these unusual observations based on a mechanism that we don't really understand just yet. Since we know that gamma ray bursts and fast radio bursts do happen quite a lot, in terms of numbers that could definitely be the case. But because these transients usually happen extremely fast, it's very difficult to explain why they would appear like stationary stars in these initial surveys. So this is definitely not the best explanation either. And so even though after the burst there might be some sort of an afterglow, at the moment the scientists are not entirely sure if this is actually possible at all. And so even though the most likely explanation is still some sort of a nova or supernova, just the sheer numbers of the objects discovered so far really make this a somewhat difficult explanation to accept. As a matter of fact, most of the collapsars or any other similar supernova only happen approximately 3 times per century in a typical galaxy, so discovering them in just a few years would be almost impossible. And so at the moment there's no one good explanation for all of this. And as I mentioned before, after examining approximately 12,000 candidates, they've officially identified approximately 800 of these objects. And so what is it? Is it some sort of an alien civilization covering stars, making them invisible? Is it some sort of a strange black hole phenomenon that we cannot currently explain? Or is it something entirely different? Well, as I mentioned, at the moment there's really almost no way to answer this. They seem to be there, they seem to be vanishing, but at the moment we don't even know if it's all the same phenomenon or if it's actually completely different phenomena that seem to be visible in a similar way. More importantly, they're not even nearly done yet. So they've examined 12,000 candidates, but in total approximately 150,000 candidates were discovered in the initial report. That means that less than 10% of candidates were examined so far. So much more is to be done, which also implies that many more such objects will probably be discovered in future studies. But as I mentioned, this is a citizen science project, which means that you can also join if you'd like to participate. So how do you join and what exactly do you need to do? Well, the website, the link is in the description below. And just like with a lot of other citizen science projects, this is basically a mini game. You can check out the tutorial to find out how all of this works and what exactly you have to do. But in short, you're given two pictures, one on the left and one on the right. And this is the old Navy pictures, this is the more recent pictures from various surveys. And basically you're trying to find out if the object in the picture is still there, or if the image is bad in some way and cannot be used, if the object has moved, or if it vanished, or maybe something else happened entirely. So in this particular case, the object is definitely still there. So some objects like this one right here are not going to be stars, they're going to be galaxies. These ones are relatively easy to identify and relatively easy to confirm that this is still there as well. And that's basically kind of all you have to do. Now, it's not a super fun game, but it definitely helps the scientists to go through those 150,000 candidates. But how do you know if the object truly disappeared? Well, here, after a few minutes of doing this, I seem to have found one. So notice this part right here. And if we combine it with the other picture, notice how it seems to be no longer there. Now, it's possible that it moved somewhere, but for all we know, it's a vanishing object. So I'm marking this as something that vanished. And to be honest, this is probably one of the most exciting projects right now, investigating something that nobody has a good explanation for. Obviously, it could be aliens, but it could also be some really unusual phenomena we never considered, something that might have an explanation in the next few years. And because all of this only started a couple of years ago, at the moment this is definitely one of the most exciting astronomical projects out there. Something that I'm pretty sure we'll be talking more about in the next few years. So since there's really no explanation and nothing else to mention here other than maybe participate in this project, there's really nothing else I can add. It's a really intriguing mystery, probably one of the biggest mysteries out there, but a really intriguing discovery that I'm sure a lot of scientists will be talking about in the next 10 or so years. Hello wonderful person, this is Anton, and today we're going to be discussing a very interesting resolution to a somewhat interesting mystery in regards to extremely ancient stars, with some stars being potentially older than the universe itself, or at least it seemed that way. And all of this is going to be based on this relatively recent study that, as always, you can find in the description below, that was able to identify very specific objects somewhere out there in our galaxy, several different objects, that seem to explain how such unusual stars are created and why they seem to exist to begin with. But first, let's actually identify what this unusual mystery was up until now. So obviously, in the last few decades, we've discovered quite a lot of different stars, and for every typical star we've discovered, there's always some unusual exception to the rule or some star that just doesn't make sense. In this particular case, some of these stars happen to be white dwarfs. Now, we generally understand how white dwarfs are formed. For example, a star like our Sun, or actually 97% of all of the stars in our galaxy, once they get old enough and once they lose their outer shell, will end up as a typical white dwarf, which represents a kind of a leftover or a core of an ancient star, mostly made out of what's known as the degenerate matter. It's basically made out of a lot of electrons condensed in extremely small space, with some of the other particles moving here and there as well, producing the total mass of this object. We've discussed this in some of the previous videos on white dwarfs. In general, though, white dwarfs tend to also be around a very similar mass. Usually, on average, they're about 0.6 masses of our own Sun. And that's because for a white dwarf of this mass to be produced, the star has to be a little bit more massive than the Sun, and obviously has to live out its life that's usually around a few billion years. So for example, for our own Sun, that's actually going to be over 12 billion years old when it turns into a white dwarf. It's going to produce an object that's about 0.6 masses of the Sun as well. With some of the other well-known white dwarfs, such as the closest one to us, Sirius B that you see being pointed at right here, being even more massive, closer to approximately 1 mass of the Sun. And that of course means that the original star was much more massive and was very likely closer to about 3 to 4 masses of the Sun before it turned into a white dwarf, which also means that it most likely lived much less, probably only 4 to 5 billion years. And that's the general relationship here. The more massive the white dwarf, the more massive was the progenitor star and the less lifetime it probably had. And vice versa. If you find a very small white dwarf, it means that the original star was probably extremely long-lived. Which creates a bit of a problem, because we've actually found quite a few of these really low-mass white dwarfs that currently do not make sense. As a matter of fact, and not so long ago, the scientists have even discovered a white dwarf that was only about 15% the mass of the Sun. And for this type of an object to really exist, in theory, the original star would have to also live for possibly hundreds of billions of years, if not a trillion years. Which obviously does not add up with our calculations for the total age of the universe, which is currently at around 13.8 billion years. And so that's basically the mystery. How could such unusually low mass white dwarfs exist? Now, the proposition a few years ago, or actually closer to like a few decades ago, was that, well, maybe they're all part of what's known as the cataclysmic variable. Essentially a binary system where one star steals the mass from the other. And in this case, it's the white dwarf that gets its mass stolen, thus decreasing in mass and increasing in size. And specifically here, you would have to have another object, such as for example a neutron star, stealing the mass from the white dwarf itself. Now that was the proposition and that was the theory, but it was very hypothetical and did not really explain some of the other white dwarfs. And specifically some of the other systems that did not really have a neutron star or did not have a black hole to steal the mass from the white dwarf. Nevertheless, the assumption was still there, and it just required some sort of a proof. It required a proof for the existence of these pre-extremely low mass dwarfs, or ELM white dwarfs as they're also known. And that's pretty much exactly what this new paper is about. It's an official discovery of several of these pre-ELM white dwarfs that explain how they're made and sort of solve the mystery of these extremely or potentially extremely ancient stars. They're not ancient at all, they just basically lost some of their mass because of their partner. But to get all of these pre-ELM white dwarfs, the scientists had to go through roughly around 1 billion different candidates, or essentially search the catalog of 1 billion different stars in the Gaia catalog that's publicly available. Out of this billion stars, they were able to discover roughly around 50 potential candidates, and in those 50 candidates, they did a direct observation and a follow-up on 21 of these objects, with all of them turning out to be these unusual formations. Now, why is it 21 out of so many different stars? Well, it's most likely because this is an extremely short process. Or basically, this is just a transition stage that happens extremely quickly, and we simply just got lucky seeing some of them in that particular transition stage. But in this particular case, it's actually a discovery of a completely new population of a specific transitional binary stars that seem to always end up producing these low mass dwarfs. But in order to be this low mass white dwarf, the white dwarf has to be roughly around 30% the mass of our Sun, or even less. Anything over that mass usually can be explained using modern physics without really needing to have any unusual star formations. But in order for this ELM to be produced in this way, or basically in order for the mass to be stolen from the white dwarf, this particular object, the white dwarf, cannot actually be denser than the star itself. Because of the density, normally the matter is going to be flowing away from the low dense object into the high dense object, or the white dwarf. Which is why usually in these formations known as cataclysmic variable stars, you'll have a low dense and a high dense object, and the high density object is the one that's stealing all of the mass. So for white dwarfs, this has to be something that's a little bit more dense than them. And for white dwarfs, it means two things. It has to be either a neutron star, a black hole, or potentially another white dwarf that's slightly more massive and thus a little bit more dense. And that's pretty much exactly what the scientists have discovered. They've discovered a few of these white dwarfs that were way more puffed up and bloated, and seem to also be somewhat egg-shaped because of the interaction with the object that's a little bit more dense and is still in their matter. But in this case, this right here is that white dwarf. This is the low mass white dwarf that's essentially losing a lot of its mass and is turning into something a little bit different. In this case, it's not an ELM just yet. It's what the scientists in this paper refer to as the pre-ELM white dwarf. But that's obviously not a very catchy name, so I'm sure in the future someone will propose a much better name for these unusual transition stages. But more importantly, the scientists have identified 21 of these objects, meaning that it's something that seems to be an explanation for how the white dwarfs will turn into low mass white dwarfs, and what exactly actually happens to them, both physically in terms of appearance, and of course morphologically in terms of the actual shape of the star. And from the objects discovered, 13 of them were still actually actively losing their mass to their partner star, whereas the other 8 seem to have just stopped transferring mass and have sort of started to transform into something else, very likely changing their shape once again, and thus beginning a transformation into an actual low mass white dwarf. with most of these objects discovered also being extremely hot, nearly 8000 Kelvin. But at the same time, some of these objects also appear detached where the mass transfer sort of stopped. And in this case, the scientists believe that because of the extremely high temperatures, this causes what's known as magnetic braking, where it basically breaks apart this transfer of mass because the high temperature prevents some of the magnetic forces from allowing the mass to transfer effectively. And so with some of these hot objects, they very likely just completely stop transferring mass and start transforming into something different a little bit early on. But the most important discovery is of course the fact that these objects were even found. It's an important evolutionary link when it comes to star transformation and explains one of the bigger mysteries without needing to have any exotic explanations. But in their paper, the scientists also mentioned that, well, if it wasn't for the availability of all of this data, this would never be even possible. Specifically, the data created by all of the teams in the ZTF or Zwicky Transient Facility and the data from the Gaia telescope that's been sort of mapping the entire galaxy, or really the entire universe, for the past few years. And so all of these incredible recent discoveries are really because of the availability of all of this data, which makes it relatively easy for a lot of scientists to then try to combine this, discovering something really cool in the process. Hello wonderful person, this is Anton, and today we're going to discuss yet another discovery that points at a mystery in the universe. The mystery of what's known as parity. Something that I'll have to explain to you in a few seconds. But in short, what was recently discovered by the scientists in Japan suggests that the universe has a preference for sides. It's essentially sided, it's not symmetrical. And this is something we currently have no idea how to explain. But let's take baby steps here and talk a little bit more about this idea of parity or symmetry of the universe. And I actually wanted to start with the idea of mirrors, which is why I've shifted myself left and right, showing you that both left me and right me were actually identical. I think most of you probably had no idea that you were looking at the mirror version of me. And this idea of symmetry goes beyond just simple description of something that's essentially an object. It also applies to different things in physics, and especially different types of features and different types of forces. For example, when it comes to physics, the scientists always believe that there is an idea of time symmetry, there's an idea of charge symmetry, and also the idea of parity. Now, time symmetry, essentially that time can flow either way and it's hard to tell apart which way is what. Or in other words, that you can technically mirror the time in both directions and you're not going to be able to tell which way is right, has actually been disproven many years ago. The idea of charge symmetry, or basically the symmetry between different charge interactions, has also been disproved with at least a few experiments. Or to be more exact, we've found actual examples where both time symmetry and charge symmetry didn't really work anymore. But the idea of parity, also known as the coordinate system symmetry, is actually what we're going to be talking about today. And once again, the best example of this parity is right here, and right here. So because I reversed myself, or basically because I created a mirror image of myself, the physicists would refer to this situation as p-symmetry, or parity symmetry. It's a pretty complex term, but that's basically what it means. To give you a more textbook example, here's a clock, a normal clock, and here is a symmetrical clock in a mirror. Both of them are p-symmetrical. And you can see that here from the 12 o'clock we go to 3 o'clock, and it seems to happen on both sides. In this case, p-symmetry seems to work and this object is definitely symmetrical. But here's an example where p-symmetry is broken, because here in the mirror clock, the situation is a little bit different. It goes from 12 o'clock to 9 o'clock. In other words, the mirror image of the coordinate system is definitely not the same as the original image. We can also refer to this as p-asymmetrical object or p-asymmetrical event. But forget about the actual terms. The idea is that, well, some things are exactly the same in a mirror image, but some things appear to be different and you can actually tell them apart. And for many years, especially in the early 40s and 50s, many scientists believed that all of the fundamental forces and all of the basic ideas in the universe were all p-symmetrical. In other words, if you were to take a look at, for example, a gamma ray, and were to then reflect this gamma ray in the mirror, it would actually appear exactly the same and you would not be able to tell which one is what. And the reason I'm using gamma rays here is because these experiments have been conducted and gamma rays are indeed p-symmetrical. And back in the 40s and 50s, many different scientists wanted to actually find out if everything else is symmetrical. But curiously, even though a lot of experiments were conducted with the strong force, the electromagnetic force, even the gravity, a lot of scientists made an assumption after this that indeed everything in the universe was p-symmetrical. But there were two scientists that were not happy with this. Two Chinese-American scientists working in the US who were not actually satisfied with the idea of maybe everything is symmetrical. They wanted to be absolutely sure. And having come up with a theory, they asked this lady right here, Dr. Wu, who was also a very famous Chinese-American theoretical physicist, to create an experiment and to test this idea. And as the story goes, Dr. Wu actually decided to postpone her vacation, created an experiment, and found out that apparently something strange was going on with the weak force after all. Now, weak force is more or less difficult to measure, and it's actually kind of difficult to come up with these experiments. But she devised a brilliant experiment that today is known as the Wu experiment, where she took the atoms of radioactive cobalt, which was known to produce beta decay, which is essentially something that weak force produces. And in this experiment, she managed to align all of these cobalt atoms in a single direction and observe the emissions of beta rays and also gamma rays. And what this was supposed to show is that here p-symmetry should have also been observed. There should have been an equal amount of gamma rays and beta rays on both sides of the detector. But time and time again, the experiment showed that there was significantly more beta rays on the left side compared to the right side. In other words, the weak force was indeed p-asymmetrical, which back then, when it was just discovered, really confused a lot of scientists, and even the famous Nobel Prize winner Wolfgang Pauli back then exclaimed that this was complete nonsense, none of this made sense, and it was probably not true. But turns out Wu was correct. This was actually something that's indeed happening, and we know today that weak force indeed violates this so-called parity symmetry, or in other words, that not everything in the universe is symmetrical after all. Although unfortunately she never ended up winning the Nobel Prize, even though technically she should have. Even though the theoretical physicist whose idea she was testing did win it after all. But honestly, Nobel Prize is known for having a lot of controversies, so that's not really surprising. Okay, well, so following all of this, what does it have to do with anything that we're talking about today? Well, it turns out that something else was found to violate this so-called symmetry or parity. The universe itself. Because by studying the oldest light in the universe, the Japanese scientists discovered something unusual about it. It was actually shifted a little bit. In other words, it was once again because by studying the oldest light in the universe, the cosmic microwave background, the scientists who wrote the paper you can find in the description below discovered something unusual about it. It was slightly polarized, it was actually shifted to one direction. But to identify all of this, here's what the scientists did. They used the image produced by the Planck telescope of the cosmic microwave background, and they essentially tried to identify the overall polarization of light coming from very far away distances, but then also comparing these values with something we knew for a fact did not have any polarization in it. Oh, quick reminder, polarization refers to a kind of a twisting of light where the actual electromagnetic wave starts to turn either clockwise or counterclockwise. Normally this is caused by interaction with somewhat powerful electrons as the light passes through some sort of a medium. And though in general usually light is produced in all sorts of different directions, it can actually become polarized in a certain direction when it interacts with something. Essentially, it does get polarized when it, for example, hits an object or if it passes through a certain medium. Here's actually a really good example of how sometimes polarization can be used in astronomy to, for example, study what sort of things are happening on a certain object. In this case, as the light strikes this planet, it actually becomes polarized and moves toward us with a specific polarization. But this polarization can actually shift as well, as the light passes through other media. It's actually a really important and very deep topic in astronomy, and so it's used for a lot of different discoveries and a lot of different analysis. And we know today that certain parts of the cosmic microwave background are polarized because essentially the light passed through something extremely energized on the way to Earth. But in this particular paper, the scientists decided to study something a little bit different. Not a specific region of the CMB, but the polarization of CMB in general, by trying to discover this angle known as beta, which refers to that shift of the angle of the polarized light. And what their initial study suggests is that there's about 99.2% chance that overall the CMB light is indeed twisted for some unknown reason. Not just parts of it, the entire thing. And what this of course suggests is that if we were to, for example, take our universe and to then also flip it as well, it would look completely different from the original universe we were looking at. There would be visible differences. Differences that currently we can't even begin to describe. But that is of course a very preliminary discovery, and it needs to have a lot more confirmation before it can become a fact. As a matter of fact, the certainty in this paper is only about 99.2%. In physics, you're required to have 99.999995% before it can become a fact. So unfortunately, this study hasn't really met the confidence level yet, but it did discover something very interesting and very unusual. Something that suggests the universe itself might not be p-symmetrical. It might have a preference for one side over the other side. And to make sure that this was not a fluke and not some sort of a mistake, what the scientists in the study did was essentially compare the detection of light coming from the Milky Way compared to the CMB light coming from faraway distances billions and billions of light years away. And it's this distant light that seemed to possess this unusual angle, suggesting that the light was polarized by something. And that something could be, well, it could be dark matter, maybe dark energy, or it could be the universe itself. In other words, one of the implications in this study is that, just like the weak force, maybe the universe also has a preference for one side over the other. And obviously, just like with the weak force, we don't really know why it does so and what's actually causing any of this. And if by some chance this is indeed what's happening with the universe, it could finally help us explain why, for example, there is so much more matter, actual matter in the universe, than, for example, antimatter, why antimatter seems to be absent. Despite being a strange discovery, this violation of symmetry can help us explain a lot of anomalies that we really can't explain in any other way right now. But because this is the first such paper and this is the first discovery, we still need to have several more confirmations and additional studies trying to discover what's actually happening here and what this may mean to the universe at large. And so hopefully in the next few years, we'll be able to either confirm or disprove this idea and then hopefully get something else out of it. Until then though, that's kind of all I wanted to mention. It's a very interesting discovery, it's a very unusual mystery, but this mystery could help us answer a lot of questions about the universe. Hello wonderful person, this is Anton, and today we're going to be discussing yet another new mystery in regards to fast radio bursts, also known as FRBs. With the new discovery coming from the iconic FRB that was discovered back in 2012, the one currently referred to as FRB 121102. And so in this video I wanted to discuss exactly what the scientists discovered and what implications this discovery has on our understanding of these unusual phenomena. First, quick reminder. Fast radio bursts, just like the name implies, are extremely fast, usually just lasting a millisecond, and are bursts of energy in radio frequencies. And one of the main reasons we've only been able to discover them in the last decade or so, and the reason why nobody knew about FRBs until 2007, is because the technology was just not there. For example, today we require very powerful graphic cards and extremely powerful computers in order to process a lot of these radio emissions in real time. And so in order for us to be able to process and catch a lot of these extremely fast radio bursts, we do require very powerful computers which just did not exist back in the days. Which of course led to a lot of other incredible discoveries in radio astronomy, many of which we've discussed on this channel in some of the previous videos. But as of today, FRBs have to be the most mysterious and probably the most poorly understood phenomena. And one of the main reasons why they're so poorly understood is really because nobody actually knows what forms them. So at least in theory, some of them could be formed by various types of magnetars, very highly magnetic neutron stars. In this case, any kind of an eruption from the surface of a magnetar on the way out will most likely also interact with the magnetic field of the magnetar and thus produce certain radio waves. And because all of this happens extremely fast, this is one of the ways that fast radio bursts could be potentially created. The discovery from just under a year ago of a magnetar here in the Milky Way galaxy that was emitting both X-ray bursts and fast radio bursts sort of proved this idea. But a lot of other FRBs seem to be very different from the FRB detected coming from the Milky Way galaxy, which of course implies that these phenomena could be generated in a lot of different ways. Nevertheless, quite a lot of amazing discoveries have been made in regards to FRBs, with many of these discoveries helping us sort of get closer and closer to the final answer of their origin. For example, one of the recent calculations in regards to an average FRB suggested that an FRB produces just as much energy in 1 millisecond as our Sun does from the entire surface in approximately 3 days. Although we also know that, generally speaking, the FRB energy does seem to vary quite a lot. So for example, the one from the Milky Way galaxy, in comparison to some of the other ones from very distant galaxies, was actually extremely weak. Whereas some of the ones from distant galaxies billions of years ago seem to be extremely strong, producing way more energy. We also know that for some reason some FRBs only have happened once, whereas a few of them discovered so far have been actually repeating FRBs. They've been occurring once in a while. And there are at least 2 major FRBs that have a very predictable pattern. There's this one FRB we've discussed over a year ago that seems to have an extremely precise repetition pattern of approximately 16.35 days. When it was originally discovered, this actually blew everyone's mind because nobody expected anything like this. But a little bit more recently, another really famous FRB that I showed you previously, the one known as 121102, has also been found to have repetitions. It seems to have a pattern of approximately 157 days. And more specifically, it seems to stay active for approximately 3 months or about 90 days, following which it stays completely silent for exactly 67 days. But exactly why it does so and the actual explanation behind these patterns at the moment is beyond our explanation. But the last 2 years have been extremely productive for detecting various FRBs, with this year 2021 being particularly lucky for a lot of different scientific teams. Mostly because a lot of radio dishes out there started to actively look for fast radio bursts and try to actively discover them using various surveys. One of the most famous and I guess one of the most sensitive surveys right now is the one conducted by the extremely large telescope located in China, the telescope known as FAST, 500 meter aperture spherical radio telescope. Since the demise of Arecibo Observatory, FAST telescope has basically become the go-to telescope when it comes to radio observations, and being the largest and the most sensitive radio telescope, it's been really successful at detecting a lot of different stuff. In June of 2021 alone, it detected approximately 500 different bursts. But very recently, in October of 2021, the scientists using the telescope reported something that's basically record-breaking. Something that you can learn more about from this paper in the description below. Back in 2019, this telescope collected a lot of data coming from the exact galaxy where FRB 121102 is located. The galaxy located approximately 3 billion light years away from us. And by analyzing the data representing approximately 47 days of observations, the scientists detected 1652 FRBs coming from this region. Specifically the exact same spot where the original FRB was detected as well. And these 1600 signals were detected in just about 59 hours of total observations, with at least 1 hour during the observations being extremely hyperactive. 122 fast radio bursts occurred during that hour. That's basically 1 every 30 seconds. But despite this detection, once again, still no explanation for what exactly is happening here. But because of this observation and because of the number of bursts detected, this allowed the scientists to sort of narrow down some of the potential candidates. For example, every single one of these bursts was extremely highly polarized, approximately 500 times more polarized than a typical FRB. Polarization of light in this case refers to the overall twisting of light as it travels away from the object. In this case, it's believed to be caused by extremely powerful magnetic fields. And because magnetars generally produce most powerful magnetic fields, this is sort of why this could be one of the potential explanations. Or maybe some sort of a really powerful black hole, or possibly some other extremely magnetized pulsar. For example, a pulsar traveling through an ancient asteroid belt has a potential to produce some of these signals. Basically, each of the asteroids as it hits the surface of the neutron star might be able to produce these fast radio bursts. We've discussed this mechanism in one of the previous videos. But this would unfortunately not explain the periodicity. Why exactly does this happen only for about 90 days and then stay silent for about 67 days? Well, one explanation here is in regards to this being a binary. Maybe the neutron star or a magnetar is orbiting some sort of a massive star that once in a while covers the magnetar, and so we're unable to see what it's doing. but in this case we should maybe see some other periodicity. So basically, if this is an orbital system where things are orbiting around one another, there should be some other patterns and some other periodicity in some of these bursts that we've detected so far. And so the scientists behind this recent paper did exactly that. They took all of these over 1600 signals and then they tried to find out if there's any periodicity or any patterns in between the various bursts that were detected. And, well, unfortunately, they haven't found anything. There doesn't seem to be any pattern or any periodicity, and the signals, for the most part, seem to be kind of random. Which also suggests that any kind of an alien explanation or some sort of megastructure is also out of the question. But how exactly did they come up with this conclusion? Well, the reason here is pretty simple. If this is a magnetar or a neutron star or a pulsar, it's going to be spinning really fast. And so basically it sort of acts like a lighthouse. And because of this, if it's spinning and if things are hitting its surface, we should be seeing the same repetition, same periodicity produced by the effects of the spinning surface. But nothing was detected coming from this object, even though the data represented approximately 59 hours. And because of the lack of periodicity coming from this object, the scientists now believe that this is probably not coming from a magnetar or from a neutron star, even though it's coming from somewhere where the magnetic fields are extremely powerful and something that does have this longer periodicity of 157 days. Or, in other words, this is now even more mysterious than before. It seems to be extremely powerful, there seem to be a lot of these bursts formed pretty much every single minute, but whatever is causing these bursts is more or less beyond our current explanations. And remember, these are really powerful events. These are very powerful bursts, and some of them happen at least twice a minute. But what can be possibly causing these? At the moment, nobody has any explanation. The conclusion from this paper is that it's very likely not magnetars, and that was of course our first primary explanation. And interestingly, a few months ago, this other study we've discussed, that should be popping up somewhere right there, has used these pictures from Hubble telescope that were able to trace some of the FRBs to specific locations in various galaxies. And here too, the scientists established that the locations suggested this was probably not coming from magnetars either, even though some of them also were coming from very highly magnetic environments. Which means that this mystery has now intensified. It seems to be even more unexplainable than before, with one of the mysteries being what exactly is producing these ridiculously powerful magnetic fields if it's not a magnetar. Which also means that we're back to where we were a few years ago, having absolutely no idea what's going on here. But this is of course why it's so exciting to follow these new studies, and why I still believe that it's basically the golden age of radio astronomy. We're discovering so many new incredible mysteries, and all of them are coming from various radio telescopes. Hello wonderful person, this is Anton, and today we're going to be talking about another discovery coming from the Milky Way galaxy. A discovery of some really unusually large structure, possibly one of the largest structures discovered in the last few years. But what exactly this structure is, and how it was formed, is not something we can actually answer right now. And that's because even right now the scientists are not entirely sure what they're looking at. On the one hand, it could be some sort of a large gas filament, a huge amount of gas, thousands and thousands of light years in length. But on the other hand, it could also be a galactic arm, which I guess is sort of possible and would mean that our galaxy now has an extra arm. But all of this is currently unknown to us simply because this is a completely new discovery. So let's start with what we know. Let's start with the discovery and also with what we know about the galaxy itself. Now, generally speaking, because of our location within the galaxy, it's almost impossible for us to see what the galaxy looks like or to try to imagine what the shape of the galaxy even is. As a matter of fact, it took decades and decades of three-dimensional analysis to sort of figure out that our galaxy was most likely a spiral galaxy with several arms, possibly somewhat similar to some of the other galaxies such as the Andromeda. But the scientists did not figure this out by looking at stars or by looking at star motion. They actually figured this out by looking at something entirely different. The motion of hydrogen gas, and specifically here by measuring what's known as the hydrogen line. Hydrogen line refers to an extremely specific frequency of 1.42 GHz that's occasionally emitted by a hydrogen atom when the electron goes through its spin change. The actual process is sort of complicated for a single video, but we know that this is a fact, and we know that these hydrogen lines are emitted by hydrogen gas. And because the hydrogen line emissions are so specific, the actual frequency is so specific, the changes in the frequency allow the scientists to measure how the gas moves across the galaxy, which allowed the scientists to do a lot of things and a lot of different calculations in regards to the Milky Way. First of all, it allowed the scientists to calculate the speed with which our galaxy was spinning in different parts of the galaxy. This is known as the galactic rotation curve. At the same time, by using the estimates from the rotation curve, they could then start using this data to try to calculate distances to various objects and to various galactic arms. Over time, this allowed the scientists to work out the general structure of our own galaxy, identifying the 4 major galactic arms present in the Milky Way galaxy. Or in other words, the scientists realized that our galaxy, the Milky Way, seems to have 4 major galactic arms. It would sort of maybe look like this if you were to look at it from the outside, although in this case, there would also be a lot of material around the galaxy as well. But over time, they also discovered some additional arms that were sort of partial, or they were not really complete. For example, there's one right here, the so-called new outer arm, and there's also a tiny one right here known as the Orion Cygnus, which is, by the way, where the solar system is located as well. And so all of this was essentially done by measuring various gas moving across the galaxy, and specifically identifying the location and the velocity of the gas. And because all of this just requires a radio telescope, it essentially can be done from any part of the planet. These types of radio waves usually go through our planet and can be detected by any radio telescope pretty much anywhere. You can technically even build one yourself. The frequency here is not very different from a typical Wi-Fi antenna or from a typical antenna used in telecommunication. But naturally, for some of the more detailed observations or for something really far away, you would require a pretty large telescope. Maybe even the largest telescope. Like, you know, the one in China called FAST, the one that we can sort of check out by using Google Earth and by looking at it from a distance of a few hundred meters. This is the largest radio telescope we have right now. It's approximately half a kilometer in diameter. And having become fully functional and fully operational last year, this is now probably the most exciting radio telescope on the planet, especially because Arecibo is no longer operational. And so by using this telescope, the scientists behind the paper you can find in the description below decided to see if they can find some unusual hydrogen lines somewhere else out there. And they seem to have identified something they refer to as the cattail. Or is it cattail? I'm not sure. Anyway, so they found something. And that something is in a very strange location. Sort of somewhere right here. Now remember, we are in this region. So this is almost on the other side of the galaxy, which would kind of make sense that we didn't actually get to see it before. And it's also pretty far away, roughly around 72,000 light years away from us. And so literally on the outskirts of the other side of the galaxy. And that's of course the region that we don't really get to see much, we don't really get to study much, but also a region that's probably hiding a lot of interesting things. With this one potentially being one of them. But before we go on, well, let's talk about the discovery from last year. Last year I've talked about the discovery of what the scientists referred to as the Radcliffe Wave. This was an unusually large formation several thousand light years in length that seemed to be super close to our own planet. And it was always there, but we've only discovered it last year. And that's because our techniques and also our instruments have improved so much that we can now see things that were always there, but we just couldn't see them before. You can find more information in the video somewhere right there. Anyway, so it shouldn't really come as a surprise that we've discovered something else, possibly even a completely new galactic arm. Especially because even though there are 4 major arms in the galaxy, there seem to be a lot of minor ones here and there as well, with this really large one discovered a couple of decades ago. Now obviously there's no explanation for why these smaller arms exist, or actually even why large arms exist or how galaxies acquire arms, but it's clear that it's definitely possible. As a matter of fact, it's sort of important to understand that arms are not actually structures. A more appropriate definition for them would be overdensities. These are sort of like crests of waves. So just like a typical wave will create a wave-like formation with certain parts of the wave being more dense than other parts, in a typical spiral galaxy you'll find something relatively similar. And in this case, if you were to try to trace a path of a single star across the galactic arm, you'll actually realize that the material goes inside the arm, stays in there for a little bit, and then leaves afterwards. So these are not permanent objects, they're just overdensities. There's just more stuff inside of them than outside of them. But their actual origin, or why there are like 4 of them here, or why smaller ones exist, all of this is sort of beyond the explanation right now. There are a lot of different suggestions, but no specific theories explaining everything. And so what exactly do we know about this formation? Cattail. Well, first of all, the way all of this was measured is by trying to measure the velocity of this gas, and specifically the difference of velocity. For example, they've discovered that on average, certain parts of this gas was traveling at about 150 kilometers per second, but the velocity range was between 170 kilometers per second, a little bit closer to the galaxy, and 130 kilometers per second, a little bit farther away, with the total mass of material present in this gas being about 65,000 masses of the Sun. So this is a huge chunk of gas. Very likely just as big as the Radcliffe wave I previously mentioned. But if this is just a gas, or if it's just some sort of a gas filament, this will be the most unusual, farthest gas filament ever found. And it would also be very difficult to explain its origins. Maybe it's some sort of a broken down galactic arm, or maybe it was created in some other way from a galaxy that was absorbed a long time ago. Right now there's really no explanation. If, however, this is actually a part of another galactic arm, it doesn't seem to match the galactic plane. As a matter of fact, it seems to be sort of warped. And if so, something really massive must have warped it, so there's even more mystery there as well. And in terms of the actual size of this object, it seems to be about 3600 light years in length and approximately 670 light years in width. But the scientists here suggest that the length could be actually up to about 16,000 light years, making this one of the most unusual and one of the largest objects in the galaxy. And because this image sort of shows us that it's not actually connected to the galactic arm and seems to be completely by itself, right now it doesn't really have a very good explanation. But it would still not be unusual. Remember, Radcliffe wave is roughly around 9,000 light years in length. And this was hiding right at our doorsteps, so discovering something like this farther away is not really unexpected. But trying to explain this is still going to be difficult. So for example, we know that most gas filaments, especially larger gas filaments, normally are much closer to the center of the galaxy. So what exactly happened here? How did this end up so far away? But if this is not a gas filament but some sort of a disturbed galactic arm, then I guess the next question is, what exactly happened to our galaxy a long time ago to disturb our galaxy in order to sort of separate one of the arms? With the next obvious question of course being, what arm did this come from? Obviously, to disturb a galactic arm you would have to have some sort of a major collision and possibly some other major disturbance in order to actually create two arms out of a single galactic arm. But if this is a result of some sort of a massive galactic collision, well then there's a whole new set of questions that needs to be answered as well. Which galaxy? When did it happen? What exactly happened to this galaxy? And why is it that only this part of the galaxy was disturbed but nothing else? And so because of this, at the moment, Cattail provides a lot more questions than answers. Actually, everything about it is a question. At this point, I would even question the name. Cattail or Cattail? Also, where's the rest of the cat? And so unfortunately, that's kind of all we know for now. We know it's there, we know that it seems to be some sort of a chunk of gas, and it seems to be a really large piece of gas. But other than that, nobody knows where it came from. Hello wonderful person, this is Anton, and this image right here shows us a recently discovered megastructure somewhere out there in the universe. An unusual formation that's currently referred to as the Giant Arc. And just like so many other megastructures or these really large formations in the universe, this one implies that there is something about the universe we don't really understand. But let's talk a little bit more about this because there's quite a lot here to uncover. And so it's important to start with some of these smaller objects here in order to grasp the scale of the objects we're talking about. Because in this particular case, we're actually going to be obviously going outside of our own galaxy, outside of our own galactic cluster, and looking at something that's way bigger than even some of the largest objects we've seen to date. And so once we sort of leave our own galaxy, the Milky Way, we'll find ourselves looking at a distance of about 10 million light years, and this is what we usually refer to as the local group of nearest galaxies. This is where galaxies like the Andromeda are, obviously the Milky Way and all its neighbors, and some of the other less known galaxies such as the Triangulum. And here's an image that sort of shows us some of these smaller neighbors around the Milky Way, the Andromeda and the Triangulum, with some of them only recently discovered. But as we start zooming out of this and start looking at other clusters, we'll find ourselves in what's known as the Virgo supercluster. And this is of course a collection of various galactic groups all connected together and all sort of more or less moving into the same direction, with the average diameter here being approximately 110 million light years, or roughly around 40 times the distance of the Andromeda galaxy to the Milky Way. But not so long ago, the scientists looking at various local clusters also discovered that there's a larger supercluster all of this is part of. Today this is referred to as the Laniakea supercluster, and in a nutshell it sort of kind of looks like this. This is roughly around 500-ish million light-years in diameter and includes several superclusters all connected and all, once again, moving in the same direction. The direction of what's known as the Great Attractor that's located somewhere right here in comparison to the Milky Way galaxy. But because this Great Attractor is more or less hidden behind large amounts of gas from the Milky Way galaxy, it's not entirely understood what it is just yet. Nevertheless, the Laniakea supercluster, which in this image you can see in yellow, forms a gravitationally connected superstructure, a structure that's, well, essentially similar to a lot of other similar structures in the universe. But theoretically speaking, or at least in terms of our understanding of the universe and how the things form in the universe, this does to some extent represent the limit of how big we believe the structures in the universe to be. Anything bigger than this should technically sort of float apart and not be connected gravitationally anymore. However, that's not really what the scientists in the last few decades have been discovering. More and more observations from various surveys have uncovered these gigantic megastructures or superstructures that seem to defy these limits. Some of them are billions of light years in size, some of them are even larger. Yet some of them seem to actually be nothing. They seem to contain absolutely nothing on the inside. For example, what you see right here represents a void. It's a void that's roughly around 1.5 billion light years across, and it's a void that's visible in the cosmic microwave background, and this is what's known as the Eridanus supervoid. It's one of those really large superstructures that exist in the universe and does not really have a very good explanation just yet. But because it's a supervoid, it's more or less empty on the inside. But then there are actual structures as well, like for example this one right here known as the Sloan Great Wall. This is once again a gravitationally connected structure of various galaxies and various clusters that's about 1.37 billion light years in length. And when it was originally discovered back in 2003, it did create a few problems and a few concerns for the modern models of the formation of the universe. Then, approximately 6 years ago, or back in July of 2015, the scientists realized that something in this particular region about 9 billion light years away from planet Earth was also forming some sort of an unusual circular structure. Today this is known as GRB or Giant GRB Ring, and it was discovered when these unusual gamma ray bursts all came from the same vicinity, from the same direction, and seem to have been coming from a relatively similar structure of galaxies all sort of connected into a sort of a ring. Or here we're really talking about various galactic clusters, superclusters, connected in a ring-like formation. And this ring-like formation would be nearly 5.6 billion light years across, making it one of the largest structures ever discovered. But because this was discovered using gamma ray bursts, or gamma ray burst mapping that is, it's still kind of disputed, just like the largest structure discovered using this method. The largest structure is right here, and this is known as the Corona Borealis Great Wall. It seems to be about 10 billion light years in length and represents about 10% of the visible universe in terms of size. Once again, this was discovered by looking at the concentration of various gamma ray bursts all coming from a relatively similar direction, suggesting a connection of galaxies. But since its discovery back in 2013, this was still sort of debated because maybe those gamma ray bursts came from different directions and were redirected to look like they came from this direction. And so the technique known as gamma ray burst mapping is sometimes believed to be not really accurate. But nevertheless, right now this does stand as the largest superstructure or megastructure ever discovered in the universe. But for this discovery, which is the object that's about 3.3 billion light years across and seems to represent yet another connection of various superclusters together, this giant arc was discovered using a very different method, a method that does definitely represent something a little bit more accurate in terms of its detection. Here it was discovered by using the light from quasars behind this object. As the quasar light passing through various galaxies on the way to our own planet absorbed the light from ionized magnesium present in these galaxies, it left a telltale mark that there were definitely galactic clusters present in those regions. And those galactic regions were forming some sort of a giant arc that also seems to be gravitationally connected into a single object. The object that's visible right here in the simulation produced by the scientists whose paper you can find in the description below. And just like with some of the other giant objects, it's extremely difficult to explain how this could have formed Or what exactly is causing these superclusters to connect into this giant arc? According to the scientists behind this paper, it's almost impossible that this happened by chance. The probability that these galaxies aligned like this is like 0.0003%. And because this also represents about 1/15th in terms of the size of the observable universe, this does make it one of the largest giant structures ever discovered. And because of the technique used and the data provided by the Sloan Digital Survey, this makes this object an almost certain superstructure existing somewhere out there, unlike some of the previous ones I mentioned that are still sort of debated. But the problem here is, of course, well, the cosmological principle that is currently believed to be the most accurate explanation for what happens in the universe does postulate that, unfortunately, when it comes to larger structures, matter should really be homogeneous. It should not really be clumpy. It should not connect into these large structures. As a matter of fact, one of the recent papers and one of the recent studies I discussed in one of the previous videos even suggests that matter seems to be less clumpy when it comes to various cosmological structures on smaller scales. And that's from some of the discoveries on the dark matter/dark energy survey. And so in that sense, something really doesn't add up, because when it comes to larger structures, they do have a tendency to form these unusual clumpy formations and these unusual clumpy structures. Something doesn't really make sense, at least in our understanding and our current mathematical analysis of the universe as we believe it to be. So in summary, when it comes to smaller scale structures, the matter seems to be a little bit less clumpy than predicted, but when it comes to larger structures, it's more clumpy. It seems to be able to form these really large formations. And though the absolute limit for how big the structure should be is about 1.2 billion light years in length or in size, this one here is about 3 times that particular limit. So theoretically at least, it should not really exist. But it clearly does, and it doesn't seem to be a chance alignment. And so the explanation right now seems to be that, well, one, we don't really entirely understand the universe, which of course makes sense because there are still so many unexplained phenomena out there. Or the second explanation here could be that, well, maybe, just maybe, it's actually completely by chance. Maybe it is a chance alignment, and maybe it is a completely rare phenomenon that's probably going to be very difficult to find elsewhere. Nevertheless, the discovery of these particular objects and these unusual superstructures is really important in helping us narrow down the exact phenomena responsible for forming these ridiculously large structures. There are still definitely a lot of different unexplained phenomena and a lot of different mysteries out there, and a lot of different arguments to be made about how these various formations and various structures form to begin with, how they evolve and will evolve over time, and how all of this might also influence things on much smaller scales, the galactic scales that might affect us as well. So in other words, it's sort of once again the question of dark matter, the question of dark energy, and possibly the question of some other phenomena that are still being explored and understood by various experiments happening right now on planet Earth. Or the more we try to convince ourselves that we understand how the universe works using new theories, the more we realize that there is always a gap in some of those theories. Something still doesn't seem to work, and something still doesn't seem to add up. Which is of course why it's so exciting to actually live right now. There are still so many different mysteries and so many unexplained phenomena out there. Something that discoveries like this will hopefully help us understand all of this, maybe in the next few decades, maybe in the next few centuries, but maybe never. But it still doesn't mean we should stop trying. The more scientists look around and try to study all of this, the more we'll learn about everything around us. Well, for now that's kind of all we know. An amazing discovery, a really cool new technique, and something that hopefully a lot more scientists will use to discover more of these unusual structures in some of the future studies. Hello wonderful person, this is Anton, and today we're going to be talking about a discovery and an analysis of a very interesting cluster of galaxies known as Abell 3391 and 3395. The clusters that the scientists have discovered are actually colliding and are creating a perfect opportunity for the scientists to try to prove or disprove a lot of theories about the universe. And more specifically, these galactic cluster collisions are actually presenting the evidence for what we already believed about the cosmic web, the vast formation of galactic dust and dark matter that seems to be all over the universe, and seems to be connecting all of the galaxies together. But these recent observations are also showing us that this is basically how a lot of matter propagates in the universe, serving as a kind of a highway for a lot of different materials going from one place to another. Which of course sort of confirms a lot of theoretical predictions, but it's always great to see this observationally as well. Now first of all, even though the cosmic web was predicted for a very long time, the actual pictures, the first pictures of the cosmic web, have only been created a few years ago, so this was a theoretical concept for a very long time. But a lot of modern interpretations of the universe and a lot of modern theories, including of course the idea behind dark matter, actually directly rely on the existence of this unusual formation. So in a nutshell, if we were to kind of zoom out and try to imagine the universe as it sort of looks like in real life, and here this means zooming out and moving away, far away from the Milky Way galaxy, and actually looking at this picture from a really distant perspective. If we could actually see in different light spectra, so not just optical light, if we could also see X-rays and infrared observations, we would start detecting something resembling this sort of a network. A network composed of these tunnels or these highways where a lot of gas and a lot of different material always circulates and always goes from one place to another, with extremely large voids that usually don't contain much in between them. But what's been predicted for a very long time but has never really been seen is that along these highways a lot of galaxies actually move as well. Each of these central clumps right here that you see, these are different galactic clusters, and they're sort of guided by these highways, by the cosmic web, into different directions. And the more observations we seem to get from the cosmic web, the more we realize how it's really controlling everything in the universe. It seems to be guiding and leading things around. Which of course makes this the central part of the entire universe, the foundation of the universe. The universe itself sort of depends on the structure. Or at least we thought so in theory, or based on various simulations and various calculations. In reality though, this was very difficult to prove, especially because there have been a lot of alternative theories, a lot of alternative propositions, trying to explain some of the unexplained mysteries of the universe. Well, now, once again, the scientists were able to expand on one of the previous studies that was analyzing these particular clusters right here. So these are galactic clusters, meaning that several galaxies are present in them, and they seem to be colliding together. Here's what this might look like if you were to look at it in 3 dimensions, with each of the dots representing some sort of a galaxy. And in this case, the scientists were focusing on a previously discovered cosmic filament that is visible sort of right here, that's roughly around 50 million light years in length. This was discovered approximately a year ago and presented an excellent opportunity for the scientists to try to figure out what happens inside the cosmic web when various clusters move through it. And so this time, by using a lot more data from a lot of other telescopes, including infrared telescopes such as ASCAP in Australia, the Dark Energy Camera that provided optical observations, and the XMM Newton that provided the X-ray observations, the scientists behind several papers you can find in the description below were able to discover and describe a lot of interesting phenomena happening inside of these galactic clusters. Now in this particular case, they focused on this region right here known as the northern clump and the other 2 clusters visible in this image as well, and tried to work out what exactly is happening in between them based on multi-frequency observations. Now here in this particular image, it's not entirely clear. And also if you look at this in visual light, it's also not entirely clear. But once you start combining some of the other frequencies, here's sort of what we start seeing in this northern clump. This region seems to have these 2 unusual protrusions going in 2 different directions. And though it might not be entirely clear what it is right away, it was pretty clear to the scientists studying this. This was a supermassive black hole in the middle of one of the galaxies in there, and it was spewing out a lot of different materials close to the speed of light. In other words, it was an active galactic nucleus. But as you probably know, a lot of these astrophysical jets are generally propelled in 2 different directions and generally are more or less straight. They should not really have such bent formations. But in this case, something was definitely bending them pretty quickly. And although obviously it could be something to do with maybe magnetic fields or possibly some other interactions with the material close to the galaxy, the explanation given in the paper, and the more likely explanation, is that these galaxies were just actually moving extremely fast. With the main scientists even comparing this to a hair of a running girl. So in a sense, because of the velocity of the collision between these 2 galactic clusters, as a lot of galaxies in this particular cluster move toward the other clusters, their actual velocity here seems to be quite great. So great, as a matter of fact, that it's causing the astrophysical jets to sort of behave as if they were in the wind. With all of this happening along the line of the cosmic filament. And so all of these little pieces of evidence definitely suggest that the cosmic web here, or the cosmic filament that represents the larger web, is sort of guiding these galactic clusters, pushing them closer and closer to one another. But because of the distances involved, and also because all of this is in basically cosmic scales, we're obviously unable to see the actual velocity or to try to estimate motion in any other way. All of this is sort of moving sideways, so we're not actually going to be able to see any redshift or anything else. And eventually it's expected that all of these clusters will probably collide, creating an even larger cluster as a result. Something that of course was simulated many different times on various supercomputers, and something that the scientists are now pretty excited to finally observe for the first time. Well, not the actual collision, but just the signs of the collision potentially happening in the future. Now, all of this is of course extremely important because, well, first of all, it does sort of provide a lot of evidence for modern theories of cosmology. At the same time, it sort of gives us even more evidence for the existence of the cosmic web, for the existence of dark matter, and for this interplay of forces that we sort of physically kind of understand. But more importantly, it helps us explain the universe as we think it is, as this huge interconnected cosmic web of a lot of gas, a lot of different material that seems to move from one spot to another, and that seems to be guided by the web itself. Something that we're learning more and more about as we discover new things out there. But since we've only really started discovering these things in the last few years, I can only imagine what we're going to know and what we're going to find in the next decade or so. So because of this, I'm actually super excited to learn more about this in some of the future studies. Hello wonderful person, this is Anton, and today we're going to be discussing one of the biggest mysteries of the universe. Where is all of the antimatter? Where are all the anti-stars, anti-galaxies, and so on? And specifically, we're going to be discussing this recent study that might have identified several candidates for what we would call an anti-star. But let's start with baby steps. Let's talk about antimatter in general, and let's also talk about the idea that antimatter should technically be everywhere. So for example, in pretty much all of the modern theories of physics, it's assumed that in the beginning of the universe, a completely equal amount of matter and antimatter was produced initially. So basically for every single one electron there should be one positron, and for every single proton there should be one antiproton. And so it's always been assumed that there should be some sort of a symmetry in the production of matter and antimatter. But from all of the observations of the universe around us, from most of the stars we've seen, from pretty much most of the galaxies, it does seem like there is some sort of an imbalance. Or actually complete misbalance. There's a lot of matter everywhere, but we don't really see any antimatter. So for example, we're not really seeing any antimatter galaxies or antimatter stars. We're also not really seeing any other antimatter particles coming toward planet Earth. Although here we have to be really careful. Even though you can hypothetically have any kind of an antiparticle, like this is an example of antiproton, which by itself is made out of antiquarks, in reality the only difference between this and regular proton is basically charge. So in case of a positron it's a positive charge, in case of an electron it's a negative charge. And if an antiproton and a proton collide, they annihilate each other, creating a lot of energy, while occasionally also leading to the creation of various other subatomic particles as well. Oh, and a quick fun fact before I continue. Today we consider antimatter to be the most expensive material on the planet. To produce one single gram, it would cost approximately $25 billion US. So even today, NASA and a lot of other scientists have been trying to figure out if there is an easy way for us to produce a lot of this material on the cheap by possibly using some natural sources. Some scientists have even suggested that since a lot of antimatter is produced on the planet in, for example, lightning, as you can see in this image, we could maybe somehow capture that. Alternatively, we could also try to produce antimatter by using extremely fast particles and a lot of extremely fast accelerator-like conditions around the planet in various highly energetic conditions around Earth, such as the Van Allen's belts or some other locations where there's a lot of particle and antiparticle creation going on at all times. But except for this natural generation of antiparticles in the lightning, or in, for example, highly energetic conditions in the magnetic lines of the planet, or obviously in the artificial particle accelerators on the planet such as the Large Hadron Collider, we don't really know of any other presence of antimatter anywhere around our planet. We also don't really know why the universe seems to be dominated mostly by matter and the antimatter seems to be completely absent. Now, one explanation, of course, is that maybe some of these stars and galaxies are antimatter, but because they kind of look similar to regular matter, we just don't really know if it is antimatter because no regular matter is there to collide with it to produce obvious observations of sudden release of energy. But that's a really big assumption because if a galaxy is entirely made of antimatter and it collides with another galaxy made of just matter, that is going to be quite a big explosion that is probably going to be noticeable from everywhere in the universe. And we haven't seen anything like this happening anywhere. Some other hypothetical explanations involve the idea of the universe splitting into two, with matter universe following our timeline, whereas with the antimatter universe following the opposite timeline. Or basically, maybe there is a universe somewhere out there that goes in a completely different time direction that's essentially made of just antimatter, and in that universe there is another anti-Anton talking on anti-YouTube about the possible matter universe where we live. So in that sense, I mean, it kind of makes sense, but there's absolutely no proof to this, and there's basically no way for us to know any of this, other than of course just hypothesizing about it, because we're not going to be able to prove this. And there are so many other explanations, including the one I covered a few months ago, with some potential discoveries suggesting that the universe has a preference for one side, and this could explain why more matter was produced originally, initially annihilating all of the antimatter that might have been present in the universe in the beginning. Now, those explanations still need a lot more proof as well, and there's just not enough evidence for any of this yet. But nevertheless, we should still kind of see some antimatter somewhere out there. Now, a study published a few months ago hypothetically imagined what would happen if there was an entire cluster somewhere on the outskirts of the galaxy made out of antistars. They essentially imagined what would happen and theoretically tried to predict what would we actually see. What type of particles, specifically here they focused on anti-helium, would be detectable from planet Earth? And what sort of energies would we see by looking at this type of an object? But a global cluster would contain thousands if not millions of antistars. That's a big assumption. Also, a collision with such an object would produce a lot of energy. So maybe anti-cluster is going a little bit too far. But how about a single star? A single antistar? Now that is not a far-fetched assumption. Having a star that has never collided with anything is actually quite possible. I actually made a video a long time ago explaining the chances for a star collision when, for example, two galaxies collide. So today we know that, for example, when the Milky Way and Andromeda galaxies collide in a few billion years from now, not a single star will most likely collide. None of them will even pass close enough to interact with one another. There will be some interaction, but it's going to be really minuscule. And that's actually because of the volumes involved here. A single star takes up a tiny volume in comparison to the entire galaxy. So you could hypothetically, in a single galaxy, have at least one antimatter star that would never interact with pretty much anything. And when it does interact with something, it might produce some energy, but that interaction might not be enough to destroy the star and might actually be very rare. And since in the past the scientists have actually detected antimatter coming from regions of outer space, there's something going on there for sure. But can we identify antistars if they exist? And well, that's pretty much what the scientists behind this paper decided to do. They decided to figure out if we can use the gamma ray observations from the Fermi telescope to look at specific types of gamma ray light that's produced when antimatter and matter annihilates, and then try to identify locations in the galaxy where this type of light, gamma ray light, might be emitted from. Now, as I mentioned before, a typical antistar would not really, we think, look different from a typical star. It would do its own anti-star stuff, it would have its own fusion reaction, it would also produce its own energy, but it would only be possible to tell it apart if it was emitting certain types of gamma ray emissions when matter collided with it and when it emitted a certain type of frequency. Very similar to the emissions we observe here on planet Earth when, for example, various types of matter and antimatter annihilate in the upper atmosphere. And so in this paper, the scientists looked at approximately 6,000 different gamma ray points of light from various locations in the galaxy, all of them analyzed over approximately 10 years of Fermi telescope observations, and to everyone's surprise identified 14 points of light that actually did give out the gamma rays where the energy levels were usually common to antimatter annihilation. And more specifically, none of these points looked like typical gamma ray sources. They didn't look like your typical neutron star such as a pulsar, they also didn't look like what we expect from black holes, and really any other gamma ray source that is familiar to us. With the major assumption so far being that, well, maybe, just maybe, what we are looking at are these 14 possible antimatter stars. And once again, it's a really big maybe that will be investigated and investigated for many years to come. But nevertheless, the implication is still there. There's a slight chance, very small chance, that what they discovered are possibly antimatter stars in the middle of our own galaxy. Now remember, theoretically it's quite possible. I mean, antimatter can technically form chunks very similar to typical matter and thus form larger and larger chunks until they form planets and stars. But because we've never seen this before anywhere, and because antimatter seems to have so far been elusive, it's still a really big assumption. And based on the observation of these stars, they also try to predict how many antimatter stars might be in a galaxy in total. Right now the assumption is that for approximately 400,000 regular stars, there might be one antimatter star somewhere. Which surprisingly also implies that there's maybe about 1 million antimatter stars in the entire Milky Way galaxy. But that's of course just an assumption for now. On the other hand, they also speculated about the existence of these antimatter stars on the outskirts of a galaxy. And in this case, a halo of a galaxy might contain billions of these antimatter stars, something that currently would be very difficult to detect or to test. And these types of emissions could only be produced and observed if a really large chunk of regular matter, such as for example an interstellar comet, pretty much smacks right into that antimatter star. That would obviously annihilate the matter and antimatter and produce those gamma rays. But at the moment, it's still kind of almost impossible to say what exactly it is we're looking at. Obviously, these could be gamma ray sources from some entirely different phenomenon, from something completely different that could also have a really good explanation. For example, to make sure that this is not a neutron star or some sort of a pulsar, and that these gamma ray emissions are not your typical gamma ray emissions coming from pulsars, further observations of these particular points would be required using optical and also radio wave light. So if we do see a lot of radio waves coming from this region, or very periodic activity, it's more likely to be some sort of an unusual neutron star or a pulsar. So there are still quite a lot of questions to answer, and still quite a lot of evidence to collect. Nevertheless, a really interesting proposition, and a pretty interesting discovery. And a discovery that might help us get a little bit closer to solving that mystery of antimatter. Where is it hiding, what happened to it, and why is it that it's not really anywhere else in the universe, at least to the point where it's basically colliding and destroying regular matter. But in some sense it's actually good that it's not here. Obviously we don't want to get destroyed by antimatter, even though we would like to find a very effective way of producing it. Being able to produce antimatter somehow would actually solve a lot of problems for us, including problems with energy. Like I said, it's a very expensive material to make, but it's also a very useful material, something that humanity might actually be able to produce one day to take us to a completely new level. Hello wonderful person, this is Anton, and today we're going to be discussing one of the bigger mysteries of cosmology that you can sort of see circled right here. This is referred to as the cold spot. The unusually large and relatively cold area inside the so-called cosmic microwave background that for the longest time now did not have a definitive explanation. And in this video we're going to be talking about one of the potential and most likely resolutions to this mystery, or basically what exactly formed this particular spot, and just generally talk about some of the most unusual and most mysterious structures in the universe, usually referred to as supervoids. But I actually wanted to start right here with this image of what's known as the Bootes void. Mostly because back in the days this was one of the most requested videos that I never specifically made on this topic for the reason I'm about to explain. And a lot of people were basically wondering, so what exactly is the Bootes void? What is this mysterious great nothing that it's usually referred to as? And what is forming these unusually large but empty structures? And one of the reasons I never specifically made a video about Bootes void is because, well, it's just one of many voids. And as a matter of fact, it's not the largest or the closest to us. The closest one is known as the local void, and there is a video about this somewhere up there. But how exactly do these structures form, and what actually happens inside of them? And I guess the other question is, where are some of the larger ones? Well, in general, their formation is directly connected to the formation of the cosmic web that essentially sort of spreads across the entire universe and usually has the galaxies connecting to one another. In essence, the cosmic web itself sort of looks like this, and everything you see in the middle, those are different galaxies and a lot of different types of gas. But naturally, in between the cosmic web and in between all of these galaxies and all of this gas, there are these voids, or slightly emptier space that doesn't contain as much density, doesn't contain as many galaxies, and doesn't generally contain much of anything. There is still some stuff there are even some galaxies there, just not as many as inside the web itself. And a lot of these simulations made over the last few years using various supercomputers, like this one right here, known as the Illustris project, have generally been able to recreate this cosmic web, showing the scientists exactly how all of this forms, but more importantly, also recreating a lot of these structures, such as voids and supervoids, just as we see them in the real universe as well. And so, in essence, some of these empty spaces right here, these are the voids you see in this three-dimensional map of the nearby space. Oh, and by the way, just to give you perspective here, these are actually huge distances. Here it's about 700 million light years away from us, and our galaxy is not even visible in this picture, it's just a tiny blob somewhere right there. But why exactly are we talking about this? Well, as you probably guessed by now, the recent study quite thoroughly investigates and more or less definitively proves that this cold spot right here sort of represents one of the biggest voids out there that in essence answers a lot of questions, including the question I asked previously about the biggest supervoid out there, and also the question in regards to why exactly this particular cold spot even exists. Although, okay, let's actually take a few steps back and briefly talk about the CMB. So naturally what you're looking at right here is the leftover radiation, or the so-called relic radiation from the early universe. This is the first light in the universe as it traveled across the universe for practically 13.8 billion years. This light was originally created when the universe was just under 380,000 years old and basically represents the first electromagnetic radiation that was created in the universe itself. And by traveling for 13.8 billion years, it eventually sort of redshifted into the current frequencies, and even though originally it was about 3000 Kelvin in temperature, now it's down to approximately 2.7 Kelvin, so almost absolute zero temperatures. And so in essence, this is the light that's only visible in the microwave spectrum of radiation in the gigahertz frequencies, just above the radio waves. But as you can see from the map, there is quite a lot of variation, with certain parts being specifically interesting because they seem to be a little bit cooler. But the actual temperature difference here is very minute. It's about 7 microkelvin, or about 0.00007 degrees Kelvin. But it is nevertheless a representation of some sort of a difference, or some sort of a structural formation that created this particular cold spot. And here's actually what all of this would look like in the night skies if you were to somehow see all of this radiation. And since the original discovery of this cold spot a few years ago, there's been quite a lot of discussion about its potential origins. One of the more unusual sort of explanations in this case involved multiple universes. In this case, at least one scientist made a somewhat controversial claim that it could maybe some sort of an imprint from another universe that seems to be beyond our own. Something that happened before the cosmic inflation, early on in the creation or the formation of the universe. Now, because it's somewhat difficult to prove this, and because the ideas here are basically extremely hypothetical, it's practically impossible to prove or disprove this. So a better way to actually analyze this is to see if we can come up with a better explanation. If you are interested in this proposition though, you can check out more about this in the wiki in the description below. And so the much better and more widely accepted explanation in the last few years was actually in regards to the previously mentioned voids. In this particular case, it's always been suggested that there was some kind of a supervoid here, so large that it would make it probably the largest void we've discovered so far. It's been always referred to as the Eridanus supervoid. And there are several physical theories explaining how such a void would actually potentially create a cold spot inside the microwave background radiation. And so this new study decided to see if they can prove the existence of this void by using the data from the so-called dark energy survey. And specifically, they actually wanted to see if the observations from the Planck telescope that created the microwave background map could be then matched with some of the other maps, for example, produced by the dark energy survey. And this survey doesn't actually use microwave background radiation, it uses entirely different observations. In this case, it looks at various near-ultraviolet, visible, and near-infrared observations and measures the expansion of the universe using Type 1 supernova, various large galactic clusters, and various other effects, including gravitational lensing effects produced by various events. And by using this survey, in the past the scientists have actually been able to create not just the map of the dark energy distribution, but also the map of dark matter, which basically acts in the opposite way. And so some of the most accurate dark matter maps we have so far have actually been produced by this particular survey. Here's, for example, one of the most recent maps produced by the survey from 2021. And so by comparing the maps from DES to the maps from CMB, the scientists realized that they too seem to match. In the process discovering that this particular region seems to have a lot less galaxies than a lot of other regions nearby. Naturally also containing a lot less dark matter as well, fitting the definition of what you would call a void, or in this case a super void. And according to the scientists in this paper, this would be a gigantic structure, empty structure. It would be approximately 1.8 billion light years across and would be located approximately 2 billion light years away from us, which also means that it's probably the nearest such supervoid to us, or as it's referred to in the paper, the nearest underdensity to Earth, with the average density inside the void being approximately 30% less than the density of mass and galaxies and so on around it. And so once again, it's not that it's empty space, it's actually not empty at all, it's just there's a lot less stuff on the inside, which is why it creates this cold spot visible right here. But at the same time, it also seems to be cigar-shaped or sausage-shaped, and we're basically looking at it from, I guess, this perspective right here. So we're sort of facing the tunnel in this case. And although this does sort of explain everything once and for all, it doesn't explain one thing. It doesn't explain the origins or how such a huge structure was created. And mostly because at the moment all of the models do not produce any such extremely large structures. It kind of suggests that either there is something wrong with our current physical model of the universe, or for some reason the universe decided to produce this unusually anomalous object that's somewhat difficult to explain using modern physics. Either way, whatever the explanation is going to be in the next few years, the paper itself is very interesting, and the finding in this case almost definitively proves that Eridanus supervoid is basically the largest such formation close to us, and is probably one of the biggest supervoids in the universe, and actually most likely even closer to us as well. It's also not in this map right now, mostly because this is a little bit outdated. But for now we don't really know what's happening inside the void and how it was formed. Maybe there was more dark energy present in this region, and so the universe expanded a little bit faster, or maybe there are some other unexplained phenomena happening inside the void that's causing these effects. Either way though, it's definitely going to be really interesting to find out what the explanation for this is in some of the future studies. For example, one of the suggestions in the paper is that maybe there's actually something going on with the slightly weaker gravitational lensing effect that's already been detected in the paper. Whatever it is, the future will tell. Hello wonderful person, this is Anton, and today we're going to be tackling a pretty interesting and a somewhat intriguing question that was recently asked in one of the studies you can find in the description below. Can a planet have its own mind? Can a planet be conscious? And though it's not a question that's going to be very easy to answer, it is nevertheless an extremely important question for the reasons raised in this particular paper. But because this is such a complex topic, we do have quite a lot to cover here. And I guess the first thing I wanted to talk about is the idea of mind itself. First of all, we still have no idea what intelligence, consciousness, or the idea of having a mind even is. In other words, self-awareness is not really that well defined. But for this particular paper, we're going to stick to one definition. It's the idea behind self-awareness having an ability to somehow self-maintain. So, for example, when you're hungry, your body finds a way to get you more food. When you're thirsty, it finds you more water. If something is not functioning well, it finds a way to try to fix it. So this self-maintaining is going to be sort of the basis for the principle of a planet having a mind. And that's because the idea of self-awareness is a very complex topic. And I'm only going to cover just a tiny part of this because there's going to be a future video discussing this in more detail. Actually, if you'd like to learn more about this, I'm leaving some of the links in the description, but one of the most common ways of testing if, for example, an animal is self-aware is what's known as a mirror test. And just as the name implies, it's a test involving a mirror. Pretty easy test to try at home if you have a pet or something. I actually tried this with my dog and unfortunately he failed. And the way it works is really simple. Let's just say we're talking about this baboon right here. You place a tiny visible dot somewhere on its face or maybe somewhere on its body, and then let this baboon interact with a mirror. If they start acting like this is another animal, the animal failed the test. However, if they realize that not only is that this is them, but they also start to look at the dot and try to remove it, by essentially looking at the mirror itself, this would imply that the animal or whatever you're testing is self-aware after all. Here's actually a really good example of an actual test conducted with magpies, and we know that they are self-aware because they constantly try to remove a dot no matter what species of magpies this is tested on. So in this particular case, this is a self-aware species. Same has been done with several types of dolphins, whales, and a lot of different primates, and they also seem to be self-aware as well. But some animals, like for example dogs, tend to be somewhat self-aware. Some dogs pass the test, some don't. Actually, most dogs seem to not pass it, mostly because dogs are just not visual creatures. They tend to use their noses more, and they do pass the nose self-awareness test. Actually, there is an experiment that tested that as well. And so if you do have a pet at home, try it out for fun to see if your pet is also self-aware. But even this process, in terms of the actual brain function, is still poorly understood. There are certain brain parts that have been identified that seem to be responsible for self-awareness in us, in humans, but we're still really far from being able to exactly pinpoint where all of this is happening. More about this in one of the future videos. And that's because today we really want to talk about planets. Can a planet be self-aware? And the way that this argument starts is with the idea of the biosphere, with this beautiful image from NASA making a pretty good visual analogy. In some sense, biosphere could be seen as something that is alive. As a matter of fact, the so-called Gaia hypothesis that was proposed a few decades ago does kind of explore this in more detail, but most scientists today don't really think biosphere is alive like a typical organism, but they do think that the biosphere is a kind of a metaphor for an actual living being. Because here, depending on the conditions, everything sort of self-regulates. We have different organisms interacting with inorganic surroundings on the planet, and through these complex interactions of different types of organisms on the planet, the biosphere itself creates the ultimate conditions for life to stay on the planet for billions of years. And there are so many different analogies about how this works that can be visible pretty much everywhere. For example, at some point, plants started to produce oxygen by using photosynthesis. This then created a lot of other conditions necessary for other life to thrive. And over time it created different really large communities, such as for example forests, where everything becomes self-regulated. So in this case, we know that different types of forests can actually regulate everything in the forest by using the very extensive root system. So let's just say one of the trees somewhere is starving or needs a lot of nutrients, the entire system is actually going to send required nutrients to that particular tree. And these types of self-regulations and these types of activities where a lot of organisms sort of collaborate and cooperate is extremely widespread on our planet. And that's the idea behind biosphere. It's a creation of a kind of a self-maintaining system by the activity of all sorts of life on the planet. Something that naturally existed here for at least 3.5 billion years. But then we have this new introduction, us, and we tend to do our own thing. And specifically, we started to introduce a lot of other things that are slowly throwing the biosphere a little bit out of balance. So yes, there is pollution, there are a lot of other influences we create on the planet that tend to sort of change things, but in this case, it could be not a bad thing at all. As a matter of fact, this is kind of what the scientists in this paper are implying. They're implying that this is part of the evolution of the planetary system, and there's a next stage after this. So what exactly is this paper about? So first of all, the scientists in this paper suggest that there are 4 stages for all planets before they reach their ultimate stage. The most common stage for pretty much all planets we've discovered so far is the so-called immature biosphere. Something that was probably around on early Earth billions of years ago, with maybe just a little bit of microbes and bacteria on the surface, possibly some activity that could be detectable in the atmosphere, such as the production of CO2 and methane, but practically no self-regulation and no feedback of any kind. Stuff here exists, it does its own thing, but nothing is affected on the planet. And then suddenly we reach the second stage, the mature biosphere. And this is the Earth between about 2.5 billion years ago and approximately 540 million years ago. We suddenly have vegetation, we have photosynthesis, we have a lot of oxygen being circulated on the planet, suddenly we have things like ozone layer, and the biosphere becomes active and starts to maintain the habitability of the planet. Now, this is something we are hoping to find somewhere out there. Chances are we might be able to find this if this is a common activity. And in this case, you're going to start seeing some other gases like, for example, oxygen. And then we have the current stage, the immature technosphere. We now have at least one species on the planet producing stuff that produces other stuff. And that species on the surface found a way to essentially use resources from the biosphere and from possibly the planet itself to create its own way to communicate, to transport things, to produce all sorts of different materials. But during that stage, because this is a completely new thing to the planet, it sort of throws it off balance and starts to introduce new materials. In this example, we have the so-called CFCs, the materials that we often associate with the ozone hole or with being extremely powerful greenhouse gases, with some other gases also changing their balance in the system. But the problem in this case, and the reason why it's called immature technosphere, is because it's not integrated in the biosphere itself. It's not integrated in the self-maintenance of the system. It adds a lot of new things, but a lot of those new things are either not doing anything or are actually making things a little bit worse, but more importantly, it's not regulated, and it's not regulated by the biosphere. And so in some sense, this actually starts working against the other parts of the biosphere. And that's unfortunately where we are right now. But then there's the next stage that the scientists propose, and the stage we should be aiming at. And as you can probably imagine, they refer to this as mature technosphere. The ultimate aim for the biosphere and for any technologically active species living on the planet. All of the systems in place, including all of the technology, is now somehow benefiting the entire planet, with all of the energy extracted from the planet not really harming anything and actually balancing out with everything else. But more importantly, in this particular case, this technosphere now also becomes part of the biosphere. It actually starts to sort of cooperate and enhance it even more. And it is precisely at this stage that the scientists behind this paper are making an assumption that the planet becomes sort of self-aware. Well, not self-aware like we are, but basically it's able to self-maintain. It sort of acquires a mind of its own, with all of the technological emissions being balanced out by other parts of the technosphere itself, with the entire technosphere working for the benefits of the planet and thus allowing the planet to exist for billions of years more. Naturally, not something we're doing right now just yet. As a matter of fact, one of the more brilliant quotes from the paper is that, well, there is definitely intelligence on the planet, but the planet itself right now is not intelligent yet. The planet does not have planetary intelligence. It doesn't have its own mind. But here the implication is that, well, maybe somewhere out there, we might actually already see certain planets that potentially possess this mature technosphere where the entire system is integrated into the biosphere and everything is able to self-regulate. And by having a complex system with a lot of interaction on the inside, this is when we start seeing a lot of different emerging properties. And in some sense, that's exactly what happens in our brains. All of these different connections between neurons start to create us. They create the intelligence. And so in this case, the scientists believe that, well, maybe something like this can potentially happen to a planet where intelligent species develops this particular technosphere, the next evolutionary stage of a typical planet. And so just like a biosphere that was able to maintain the planet for billions of years, the next stage, technosphere, can make it even better. Although I guess one question that's going to be very difficult to answer in this case is, okay, but how do we actually get there? And how would that look like if we were to look for this using telescopes? None of those questions are currently answerable, but it is definitely something we have to try to figure out. I mean, more or less for the existence of our own species. And so one of the main purposes behind this research is to really try to figure out where exactly should we be headed, what should we be doing in order to preserve the technosphere and to make it into something that to some extent acquires its own mind. With the other implication potentially also answering the so-called Fermi paradox. If we ever find some kind of a technological civilization out there, it's probably because they found a way to reach the stage. They didn't kill themselves, reaching an actual stage of planetary intelligence. And if we'd like to survive as well, for as long as possible, we definitely have to try to use our own intelligence for the benefit of the planet as a whole. But I guess baby steps. So pretty intriguing research, very interesting study, but something we'll discuss more in some of the future videos as well. Hello info person, this is Anton, and today we're going to be discussing some of the new discoveries, some of the more interesting discoveries, in regards to gravitational waves that we usually associate with various black hole collisions. But in this particular case, the study did not study black holes. And in this particular case, the actual waves that were discovered on the planet are much longer in wavelengths, most likely created by much more massive objects or objects that are extremely ancient. And this is something that has been actually investigated for the past few years using a system of different pulsars. And so let's talk a little bit more about this particular study, what it means to our understanding of the universe, and obviously how all of this works as well. But let's start with the idea of gravitational waves, and I guess let's start with black holes. So it's actually kind of incredible to think about the fact that we only found gravitational waves or confirmed gravitational waves back in 2015. So back in 2015, the scientists finally confirmed the existence of gravitational waves created by binary black holes. Or to be more exact, created by black holes that are about to collide and form gravitational waves of different frequencies during their collision. Later on, the detections have also discovered collisions between black holes and neutron stars, two neutron stars, and potentially some other unusual objects that are still being investigated, but most likely represent even more massive black holes. And when it comes to these gravitational waves, well, it's actually kind of difficult to wrap your head around what exactly they represent. These are obviously not the same as your typical waves detected on planet Earth, and these are obviously not the waves we can usually perceive in any way. But these waves do create oscillations of space-time itself, basically making everything around us sort of vibrate without anyone realizing. And the only way of naturally detecting this, at least at the moment, is by using these very large interferometers, usually employing extremely sensitive lasers. And so by watching the actual changes in the space-time between these lasers, the scientists can generally determine if there was some sort of a gravitational wave effect. But in this case, it only focuses on very specific frequencies, with frequencies ranging from hundreds to thousands of hertz, usually representing much smaller objects, so for example, a typical solar mass black hole. And so if we wanted to detect some other wavelengths from some other larger objects, for example supermassive black holes, we would not be able to see them with the LIGO, the detector that was used for these detections. In this case, the frequencies would be much lower, sometimes less than 1 hertz. And so one of the possible solutions here in the past was a proposal of a space interferometer, known as laser interferometer space antenna, that would essentially orbit around the solar system and would try to detect the gravitational waves this way. Now naturally this is just a proposition and this doesn't exist yet, but this would in theory allow us to detect a lot of other things we've never been able to see before. But LISA would be a really big project, and it's still sort of in its planning stage, so it might actually take a few years or possibly even a decade before this is possible. But we do have other ways of detecting gravitational waves using some other really interesting and very creative techniques. One of them is from the collaboration known as nanograph we discussed a few years ago, that employs a much more sensitive and actually a much more creative way of looking at the universe. It essentially uses pulsars, or the extremely dense neutron stars that tend to produce extremely accurate pulsations, usually in radio light. And the thing about pulsars is that their oscillations are so extremely accurate that someone has even proposed to use them as sort of a more improved version of an atomic clock. So basically here, by measuring the oscillations with extreme precision, it becomes possible to then measure time. But what if you were to look at several pulsars in different locations of the galaxy? And what if you were to then compare various oscillation differences in those pulsars? And that's precisely what a lot of these collaborations have been doing for over a decade now. Nanograph is probably the biggest one. Last year it released the data from 45 different pulsars, but we also have the European Pulsar Timing Array and the International Pulsar Timing Array that have recently combined the data from 65 various pulsars, once again confirming that something is definitely going on out there. In other words, by looking at approximately a decade of data from 65 various pulsars around the galaxy, they found strong evidence indicating some sort of an ultra-low frequency signal that in some sense can be described as some kind of a gravitational wave background. It can also be sort of compared to the famous cosmic microwave background, which we know represents some of the most ancient light in the universe. Now this, on the other hand, is not visual light. It's not the light we can see with our eyes or the light we can sense with a microwave detector like in this case. This type of a detection, this type of a signal, is only visible as a gravitational wave. With the scientists sort of comparing this to the sound of a drum humming in the background, with basically the entire universe vibrating at these extremely low frequencies, or these extremely long wave gravitational ripples that seem to be all over the place. And all of this was detected by looking at various oscillations from these pulsars for over 12 years and noticing slight discrepancies in some of the signals detected from the pulsars that can be best described as essentially these waves creating ripples between us and the pulsars. And considering that in the last year this is actually one of many studies confirming these results, with a lot of other studies already focusing on potential explanations, whatever is causing these unusual gravitational waves is definitely really exciting and extremely interesting. But I guess the question is, so what could it be? What's causing these unusual, very long wave gravitational waves, and what can be the best possible explanation? Well, naturally one of the bigger explanations here would be potentially very ancient supermassive black holes colliding or slowly approaching one another, creating these extremely powerful gravitational waves. This would of course be the most likely explanation and the one that could help us explain how basically galaxies grow larger and larger by combining their black holes and combining a lot of the mass. However, interestingly, the data from some of the studies suggested that this was maybe not the best explanation to fit with what we're seeing here. Interestingly enough, another explanation was proposed in regards to the early formation in the universe that the scientists often refer to as the cosmic string that can maybe explain some of these formations as well. Cosmic strings can actually be seen as basically these unusual deformations formed in the early universe, kind of similar to various deformations that we usually find inside crystallized water, inside ice. And so just like the cracks inside ice, some of the theories propose that something similar formed in the early universe, and essentially this would be the possible explanation for these cosmic strings, and of course for some of the gravitational waves that could be created. The better explanation can be found in one of the older videos specifically on this topic, the video that you can also find in the description below. But it could also be some other unexplained process that was happening in the early universe that basically resulted in these very powerful gravitational waves that survived for billions of years. Honestly, at the moment, nobody really knows, and it's extremely difficult to say. Also, we would probably need a few more years, or actually more like a decade of new data, in order to actually confirm this first. At the moment, it's even been suggested that maybe all of this is actually due to some processes inside pulsars that we just don't really understand yet. Maybe these oscillations were created by the pulsars themselves. Or basically that it's not really gravitational waves we're detecting, we're actually just detecting different oscillations in the pulsars. Nevertheless, unlike the gravitational waves from black hole collisions, which can be described as transients, or basically events that just happen once, these particular gravitational waves we're detecting from pulsars, in essence, seem to be more or less permanent. They literally seem to be like a hum or a background noise that's always there. So once again, very similar to the cosmic microwave background. Which also means that maybe one day, once the techniques improve and once we have more observatories, the scientists might be able to create an actual map of these gravitational waves just like we have with the CMB in order to help us understand what exactly happened in the early universe and what created this gravitational wave background noise that we seem to be detecting from various studies. And actually one of the other propositions was in regards to the creation of primordial black holes. The black holes that could in theory represent the mysterious dark matter. And so by detecting these gravitational waves or this wave background, we could maybe finally find the dark matter that we're looking for. And so in essence, those are the three main propositions right now. Either the mysterious cosmic strings, possibly dark matter or basically primordial black holes, or maybe collisions from supermassive black holes that created various galaxies. Or maybe all of them all together. For now, nobody really knows. Whatever it is, it's definitely something that's been happening for a long time, and it's definitely something extremely powerful. But until we have observatories like LISA right here, it's going to be very difficult to tell exactly what's happening, or more specifically, identify where it's actually coming from. Hello info person, this is Anton, and today we're going to be discussing yet another unusual mystery about our own universe. Something that was kind of discussed a few months ago and something that we've known about for just over a few years now, but something that still doesn't have a good explanation and seems to be even more mysterious than a few years ago. We're talking about what's known as the Hubble tension. So here's how this is right now. When it comes to trying to explain the universe, there are obviously a lot of different ideas and a lot of different theories out there. But when it comes to astrophysics and when it comes to astronomy, it's the direct observations that matter. When the scientists see something, and also when they detect something that can either explain new phenomena or can potentially confirm previous phenomena, that's really when it gets exciting. Which is actually pretty much exactly what just happened now with the recent study that you can find in the description below. So let's actually kind of talk about this. And let's start with a bit of a history. So back in 1915, Albert Einstein published his famous general theory of relativity, which within only a few years becomes a fundamental theory potentially explaining the universe around us. After about 2 years, he adds a constant to this particular formula that he had, a constant that we refer to as the Einstein's constant. And the whole purpose of this was to basically ensure that the universe was static. It wasn't moving anywhere, it wasn't expanding, it wasn't shrinking. But later on, Einstein realized that this was the stupidest mistake of his life. At least that's what he called it. Because by 1931, he finally accepted the idea that it was an expanding universe after all, like suggested by some of the other scientists, including Hubble, the French Georges Lemaitre, and the Russian Alexander Friedman. And so by 1931, the formula was reworked to have a kind of a constant expansion value, suggesting that the universe was expanding constantly throughout the entire time and space. And this pretty much kind of stayed like that for a very long time. But then in 1998, which was only about 23 years ago from when I'm making this video, 3 astrophysicists, Sol Perlmutter, Brian Schmidt, and Adam Rees, identified something really unusual by looking around the universe and looking at various supernovae out there. They realized that the universe isn't just expanding, it's also accelerating its expansion. It's moving faster and faster and faster, and eventually they won the Nobel Prize for this. And so once again, it was really the observations of these unusual events that sort of allowed us to understand something else about the universe that we didn't know before. Now today, the explanation for this is the mysterious dark energy, which by itself does not really have a very good explanation, mostly because the theory and the actual observations don't really match at all. But over the past few years, as the scientists started to analyze the expansion of the universe and the acceleration of the expansion, or essentially trying to identify what's known as the Hubble constant, they started to see new patterns emerge, patterns that didn't really make sense. So some of the initial studies established the Hubble constant at approximately 73 km per second per megaparsec. This basically means that for every 1 million parsec, or for every 3.26 million light years that we travel, the universe accelerates its expansion by about 73 km per second. So that was fine and all, but then some of the other observations, using some of the other methods, for example using some of the nearby stars known as Cepheid variables, which normally blink or change their brightness quite specifically, so they actually allow scientists to establish very precise distances to various locations in the galaxy. And also by using various types of type 1a supernova, which normally explode with a very specific brightness, once again allowing the scientists to establish distances, the values started to change a little bit. At first it was 68 km per second, and then with pretty much every single observation, the values changed once again, with some of the more recent observations visible right here in this picture. And what's interesting is that some of these observations were extremely accurate. They had an extremely low error. Obviously comparing this to some of the observations from X-ray observatories or from Hubble telescope. But if you were to sort of draw a line through this, you would not be able to capture all of these observations. In other words, it was as if the values for Hubble constant were different depending on what location we're looking at or what time period we're looking at, with some of the new values that you can see right here in this table. And so something was definitely not adding up. Moreover, depending on the technique used, the values always congregated around the same number. So for example, all of these red observations you see, these were done using extremely old cosmic microwave background, and so they essentially showed us the universe long time ago. Whereas a lot of these observations in black, these were from some of the more recent events or from some of the closer regions, such as for example from nearby galaxies, from our own galaxy or from the galaxies not too far away. And so the values seem to sort of correlate with the distance away from planet Earth. And so just to see what's happening here and possibly discover some other unusual patterns, the scientists whose paper you can find in the description decided to analyze around 1,000 different supernovae from various regions in the universe, obviously created in various times around the universe, and decided to see if they could maybe connect this to some kind of a other element or some kind of a other constant. Or actually, more specifically, they wanted to see if this could be explained if the constant was not constant at all, if it was actually a dynamic value. And so by combining all of these different observations from different previous studies, and by also mixing and matching various results, making sure that there's no biases and no potential errors, they came to a somewhat not surprising conclusion that everything seemed to fit perfectly if the Hubble constant changes with time or if a kind of a time element is added into it. Or by turning the Hubble constant into a Hubble variable that varies with time, a lot of their calculations seem to match actual observations. But this is just a preliminary first study. The scientists in the study do mention that a lot more supernovae are needed to make sure that first of all there is no bias in, for example, observation. For all we know, maybe a lot of these supernovae were just kind of in the right location at the right time. Maybe if we were to turn around and look at some of the other objects, thousands of other supernovae in some other galaxies, maybe this particular result would actually disappear. And so that's kind of what the next step is going to be. These scientists will be trying to find more supernovae to study and try to see what's going on with those as well. But I guess the more exciting part is, of course, if they're correct. If the Hubble constant is not actually constant and if it has changed over time from about 68 kilometers per second per megaparsec to about 73, well, in that case, well, first of all, this does actually create a bit of a problem for many different formula, for many different estimates, and even for the age of the universe as we know it. It means that a lot of things will have to be recalculated. At the same time, this also implies that, well, there are obviously a lot more things going on here. It's either completely new physics, something entirely different nobody understands just yet, or possibly something to do with gravity that we just don't understand. One of the potential explanations here are essentially a group of ideas or theories referred to as the modified gravity theories. And here there are actually quite a lot of different explanations and quite a lot of different ideas that generally try to explain the universe without the use of things like dark matter, dark energy and so on, and instead modify formula from Einstein and from Newton, making everything fit slightly differently. But that's of course just an assumption for now, just a preliminary explanation. Chances are that maybe in about 10 years from now, just like it happened back in 1998 when the scientists originally discovered that the universe was accelerating, now someone else might end up winning a Nobel Prize for trying to figure out what's happening here as well. Nobody really knows what it is. Obviously no one has any good explanation, even though there are quite a lot of explanations, but there's definitely no one explanation that seems to explain everything we're seeing. There's always something that doesn't make sense, which of course is actually really exciting because the less we know and the less we understand, the more likely we're going to be exploring and learning and possibly discovering new things for many years to come. Because, if you actually discover everything about the universe, well, everything sort of becomes really boring. And so I'm actually super excited to keep learning about this, to keep trying to understand what's going on, and then relay all of this to you as well through these videos. Hello wonderful person, this is Anton, and today we're discussing some of the new discoveries in regards to black holes and black hole collisions. But actually, more specifically, we're discussing this study right here that makes a very interesting suggestion in regards to how black holes have a potential to increase their mass as the universe expands as well. In other words, black holes seem to be directly connected to the growth of the universe. So let's discuss this in a little bit more detail, but let's start with the mystery behind black hole collisions. This right here, by the way, is the frequency produced by the gravitational waves when two black holes collide. So prior to 2015, a lot of theoretical scientists, a lot of theoretical physicists made a prediction in regards to black holes and the black hole collisions. And the prediction was that basically we're going to be able to find them if we build a large enough detector that's able to detect very minute frequency changes in the space-time itself. And this is of course what we refer to as interferometer. And LIGO, as it's known, is the world's largest interferometer able to detect these changes in space-time. And that is essentially how we're able to detect these black hole collisions. But at the same time, other predictions involve the black holes themselves. For example, prior to 2015, the scientists also made an assumption about how many black hole collisions we'll be able to detect and what the total mass of each of the black holes is going to be. Generally speaking, in terms of mass, the black holes were expected to be way below the mass of about 40 masses of the Sun, with the frequency being maybe a few times per year. However, once the device became operational in 2015, and once these detections became a pretty regular occurrence, this is where a lot of mysteries sort of appear and became problematic for some of these previous theories. First of all, the amount of collisions was way more than originally predicted, with many of these collisions being found pretty much several times per month. But on top of this, the other major mystery started to appear in the last few years, the mystery of these extremely massive black holes. For some reason or another, a lot of the black holes detected so far had masses exceeding what was expected, with some black holes being almost 100 masses of the Sun. As a matter of fact, the formation of some of these black holes is currently unexplainable using modern physics. Moreover, some of them combine to create what's known as intermediate mass black hole, which essentially presented a lot of new mysteries and a lot of unanswered questions. And in the last few years, a lot of propositions and a lot of explanations have been made by scientists trying to explain some of these mysteries. For example, in terms of frequency of collisions, a few studies suggested that maybe what we're seeing is actually happening in the center of the galaxy. For example, in the center of the galaxy where there's a supermassive black hole, we also expect a lot of other material to orbit, and specifically a lot of other black holes. In our galaxy, we expect there to be at least 10,000 different black holes. And so the chance for collision in these particular regions increases quite dramatically. So one of the potential explanations was that, well, maybe we're just seeing these events as they happen around centers of different galaxies. In other words, we're not really seeing these two individual black holes in the middle of nowhere. Maybe these black holes are actually orbiting a much larger central black hole. And at the same time, this could maybe also explain why certain black holes are so much more massive. Maybe in the past, because of these constant collisions in these regions, some black holes just ended up being way more massive because of the constant collision with everything in the vicinity. And so this does kind of make sense. By being in the center of the galaxy, by having a lot of different black holes to collide with, we could potentially explain the mysteries that we're observing from LIGO. But not everyone agrees with this explanation, and a lot of other propositions have been made in the past. And one such proposition is from this recent paper, and it actually sort of, theoretically at least, makes a little bit more sense. And more importantly, this particular study is able to explain the unusual diversity of various collisions, specifically the diversity in terms of mass. For example, some of these black holes don't have much mass, but some of them have way too much mass. And more specifically, if you were to look at this in terms of the location where these signals came from, it sort of helps you uncover another unusual mystery. There's this really cool article that you can find in the description below, with this beautiful chart created by Nadia Bremer, that allows you to explore some of these detections by going back in time and by basically moving away from our galaxy. So right here, if you sort of look at the detections, you'll notice that the circles, or basically the mass of these black holes, is going to be larger and larger, with basically some of the largest detections so far being really far away from us. And so that by itself is also another mystery. Why is it that a lot of these larger collisions happened farther away from us and happened in much earlier universe? So you can see the biggest merger between two really massive black holes that created an intermediate mass black hole happened about 6.5 billion years ago. And so to try to explain this, the scientists in this paper focused on something that's entirely different. They focused on the idea of the black holes as they evolve with the universe. And so in this particular study, the scientists decided to focus on the influence the universe has on everything in the universe itself, including of course black holes. And specifically on how the universe changes the things inside of it by expanding and also accelerating its expansion. So in other words, here we're talking about dark energy. And this assumption is sort of important, mostly because of the way that the black holes are usually modeled. So normally when the scientists try to model black holes, they make an assumption that the universe in this case does not affect black holes, and so the universe is static. This is of course based on the Einsteinian formula. And this in a sense simplifies a lot of the equations and makes the calculations much easier. But a lot of these models and calculations normally are only good for a certain period of time. once the universe expands and once it sort of grows a little bit, the calculations and models are going to be a little bit off. But this type of simplification definitely works for black hole collisions when we're only talking about a few seconds before they finally collide. In other words, modeling this for LIGO or for any other interferometer works just fine and doesn't produce any problems. But in this case, we are only seeing the final moments of the collision. We're not actually seeing the beginning or even the middle part. The actual process of black holes colliding toward each other may take millions or even billions of years. And when we're talking about millions and billions of years, and when we actually talk about the expansion of the universe, in this case, some other effects become more prominent. One such effect is known as the cosmological coupling, which essentially implies that a lot of things in the universe are kind of connected and affect each other. So if the universe expands in size, a lot of things inside the universe will also change to some extent. And I guess the best example of this cosmological coupling is the light itself. We know that redshift or cosmological redshift is usually a telltale sign for us that something is really far away and is moving really fast from us. And so here, as the universe increases in size, the light slowly loses a little bit of energy. That's redshift in action. And so, for example, a distant universe producing a lot of ultraviolet light as it creates new stars is really only going to be producing radio light by the time that all of this light makes it to planet Earth. But in this case, the researchers made a different assumption. They made an assumption that what if black holes are also coupled to the universe? And what if the black holes over time start to gain energy? And not because they were absorbing stuff, just because the universe itself was growing in size. The scientists provide a pretty good theoretical basis for this in their paper. And to try to see what happens, the scientists modeled roughly around 1 million different stars that went supernova, with some of them then creating black holes, with some of these black holes being in binary systems that slowly started to move closer and closer to one another. But in this case, the black holes produced by supernova were pretty much exactly the ones that we expect to be produced, not the ones we observe from LIGO. And then they essentially made an assumption that as the universe expands, the black holes slowly grow in mass. And they wanted to see what the total mass of the final black hole is going to be, depending on the distance and depending on the time it takes black holes to collide with one another. And to their surprise, they've managed to sort of solve both mysteries. There were a lot more mergers detected, and a lot of these mergers were much more massive than the ones that were originally theorized by a lot of scientists before 2015. And interestingly, the scientists in the study did not change any other factors. Everything else in the universe was as we know it. And so just by itself, this presents a pretty interesting argument. The argument being that, well, black holes, like everything else in the universe, do not exist in a somewhat static, unchangeable universe. As the black holes move around, as they orbit one another, or as they do other things, they may also change as the universe expands and as the universe changes. And so by itself, it does present a pretty interesting explanation to a lot of these unusual observations. But it still obviously does not help us explain where these collisions happen, or specifically what part of the galaxy or what part of the universe. It also does not explain why some of the black holes seem to have such a big mass difference, like the ones you see right here. So there are definitely quite a lot of mysteries left to be solved. But by itself, this cosmological coupling idea seems to be able to present a lot of the explanations that were previously unavailable, and seems to be a really important concept that some of the future studies need to address. If black holes are indeed connected to the expansion of the universe, and if their mass is affected by the universe itself, this might also help us solve a lot of other mysteries and explain a lot of other observations that the scientists have been struggling to explain. And so as the LIGO observatory collects more data, we might be able to finally answer all of this once and for all. For now, it's a very interesting proposition, and a proposition that arises from solving some of the Einsteinian equations. This is actually something that appears in the general theory of relativity. Hello wonderful person, this is Anton, and today we're going to be talking about a pretty incredible discovery that suggests these incredible large massive structures in the universe that form the cosmic web seem to actually be spinning and producing the so-called angular momentum that might give other objects such as galaxies the angular momentum needed to spin as well. But let's discuss this in a little bit more detail because this is a pretty complex topic. First of all, let's establish the scale here just so that you understand how big of an object we're talking about. Once we start moving out of our solar system, we'll first find ourselves in a local cluster of nearby stars. And eventually this will obviously produce our galaxy. And pretty much all of the objects at these scales have some sort of an angular momentum somewhere. Now obviously all of the planets and all of the smaller objects in the solar system spin, also the planets themselves orbit around the sun, which is also a result of angular momentum, but even if you zoom out and look at further stars, even in various nebula or in various globular clusters, things have a tendency to spin as well. And all of this also spins around the galaxy. So this angular momentum seems to be present all the way to the galactic sizes. But what if we zoom out a little bit more? Well, first of all, we'll find ourselves in the galactic cluster. And here the galaxies do have a tendency to orbit around one another as well. And this of course means that the spin and the angular momentum is still available and still visible even at the million light year scale. However, once we zoom out far enough, specifically here it's about 100 million light years, and start looking at larger clusters, here we're talking about what's known as a supercluster, and this one being the Virgo supercluster and the even larger cluster known as Laniakea. Well, at this point, so far no spin has ever been detected. But do things also spin on larger scales as well? And that's of course one of the major questions that the scientists are trying to answer. Although, quick side note, what exactly creates this angular momentum and what exactly creates this spin? Well, on smaller scales, it seems to always happen when two objects that somehow can interact with one another, so for example through gravity, somehow pass close to each other and start interacting, thus creating the spin that you see right here that eventually starts developing into a more complex angular momentum. Now this is what happens with a lot of star formation, this also happens with a lot of galactic formation, and we also see this in liquids and in gas for example, so it does happen pretty much everywhere. Although the actual nature of this and also the actual explanations are still not really well understood. But in the last few years, the scientists also started to discover some unusual observations from various galaxies and especially various quasars out there. They started to discover some unusual patterns suggesting that certain galaxies were sort of spinning in the same direction or in the same way. I've talked about one such study a few years ago, and it essentially discovered that there were quasars along the formation known as the cosmic web that seemed to have rotation in the same direction, as if something provided the angular momentum to them, because if this was by chance, they should all be pointing in completely random directions. And this sort of implied that something else is going on these larger scales, something that seems to be guiding the overall spin of things in the universe. And so naturally it's kind of interesting to figure out if something else is going on these large scales, with something else giving the galaxies their spin. Although interestingly, a lot of these simulations that the scientists performed over the years, with the biggest one being the Illustris project, to some extent also have been suggesting a major spin going on in these larger structures. Now, which structures are we talking about? Well, we're really talking about these cosmic tendrils or cosmic web that you see right here. It's not really visible in this picture, but it sort of goes all the way here, connecting all of these galaxies together and forming this really massive formation that's been detected over and over again in various studies. For the most part, it seems to be made out of the mysterious dark matter, but it also contains a lot of different gas, some of it actually primordial gas, that has never been anything but gas. It never formed any stars, it never participated in any formation of anything, and it sort of stayed as gas for the past 13.7 billion years. A lot of this gas will never actually become anything. But some of this gas gets funneled into various galaxies and is responsible for making the galaxies around the universe become larger and larger, and also growing the black holes in the middle as well. So all of this is to some extent guided by the cosmic web. And although it's still difficult to imagine what goes on inside the cosmic web, some scientists speculated that it's sort of like these tunnels of diffuse gas, where the gas slowly is funneled into various regions around the universe, forming certain globular clusters and forming various galaxies. But the galaxies themselves also stay inside the cosmic web as well. They actually seem to be moving inside of the cosmic web, and they also seem to be spinning along the axis of the web itself. At least that's what the scientists thought, and this is what the simulations showed us. And now it looks like we do have a confirmational proof, and a somewhat unexpected observational proof, that the cosmic web indeed spins, and very likely provides a lot of the angular momentum to a lot of the structures located inside the web. And that's of course being galaxies, clusters, and superclusters that are most likely aligned along the web as well. This of course implies that even the clusters here are probably moving in a somewhat circular motion, although it will be very difficult to detect this because of the actual sizes involved. And naturally also because all of this takes a really long time. But what exactly was detected right now, and more importantly, how was it detected and how accurate are the observations? Well, the data itself came from the very famous Sloan Digital Sky Survey, with the data containing thousands and actually hundreds of thousands of galaxies. And because the structures the scientists were trying to study were extremely large in size, they essentially had to divide the night skies into tinier chunks. They separated each of the filaments into different segments and turned each of the segments into a kind of a cylinder, with the galaxies here being approximated as either being located on the part of the cylinder that moves away or the part that moves toward us. And then by carefully observing the redshift of each of these galaxies and averaging the observations depending on the location, they were able to definitively see that certain galaxies were approaching us on average at a speed of about 100 kilometers per second. Whereas other ones were moving away from us at around 100 kilometers per second. And this was of course depending on the location inside this cylinder-like formation created by the galactic web. This image right here being a pretty good visualization of the kind of a cylinder I'm talking about here. So some parts will be receding, other parts will be coming toward us. But because these structures are so humongous in size, here we're talking about hundreds of millions of light years long, and maybe a couple of million light years across, it was relatively difficult to do these observations, but naturally, because of the total number of galaxies used and because of the observations of different parts of the night sky, the average calculations indeed showed that the spin seems to be there. The galaxies were definitely moving away on average or coming toward us on average. Although at the moment, there is unfortunately no good explanation for how it's possible. Now, we do believe that overall the spin itself usually forms when there is some sort of a higher density versus smaller density of stuff. So in the universe, that's probably why certain galaxies acquired spin. But in these larger structures, it's very difficult to explain the overall spin of a tendril or a galactic web, especially because the scientists today believe that on average, larger objects in the universe should not have any spin or any kind of a curl. There's really no reason for any kind of a rotation in the early universe, at least from the models we have about the early universe. Which of course means that our models right now are very likely not entirely correct. Something out there definitely seemed to have created the spin for at least some of these cosmic tendrils. And since other studies doing other observations have also observed a kind of a common spin to different objects that are really far away from each other, overall all of this sort of starts to make sense. It just doesn't have a really good explanation yet and does not help us understand the early universe based on our current understanding of the cosmological events. And this would also of course explain how galaxies are able to spin in the same direction. It would also explain how dark matter seems to move around and how the halos in those galaxies move as well, while also helping us explain some of the other unusual observations of various types of motion across the universe, and possibly even helping us resolve certain other mysteries. Maybe this will help us explain the unusual observations of the so-called Hubble tension, although for now it's all kind of early to tell. What is really exciting though is that this is the first confirmation and the first official observation of the actual angular momentum and the actual spin of the largest structures we've seen so far. Here we're talking about hundreds of millions of light years big, which is of course like 1,000 times bigger than the entire Milky Way galaxy. But there were of course other discoveries from this study as well. For example, the actual speed of the rotation depended on the angle from which we were looking at the cosmic web, with the highest velocity detected when we were looking at this completely edge on, while at the same time the highest speed of the rotation was usually very close to massive halos of extremely massive galaxies where we expect to have a lot of dark matter as well. And the more massive the halo, the faster the rotation detected. So definitely quite a lot of interesting discoveries. Hello wonderful person, this is Anton, and today we're going to be discussing some of the new discoveries and simulations in regards to various extremely large structures in the universe. specifically structures like the Laniakea, where we are located, things like the famous Great Attractor, the mysterious structure everything seems to be headed toward, and a lot of other formations that have been discovered in the last few decades that we're still trying to learn quite a lot about. But this recent study and the selection of videos included with the study help us understand how everything evolved in the last 12 to maybe 13 billion years, and also help us understand where all of this will be headed in the next 20 billion years. So let's discuss this in a little bit more detail, but let's actually start with the idea of the scale of things here. Because here we really are talking about something extremely grandiose, something that's somewhat difficult to imagine for the human mind. I mean, for example, if we were to start escaping planet Earth and start to move faster and faster, we'll eventually reach the outskirts of the solar system. But moving at this velocity, it will take us a really long time to get where we're going. We now have to accelerate even more to try to escape the galaxy. And even here, we're still not even close to, once again, our destination. We have to keep moving and moving until we start seeing the collection of galaxies and various nearby and distant galactic clusters. And at some point, once we reach the distance of about 350 million light years away from us, that's basically where we have to start. We're now looking at different galaxies and specifically various galactic clusters that make up Laniakea, the superstructure that we're part of. This was discussed in one of the older videos on the channel that should be somewhere right there or in the description, but in a nutshell, it's basically a lot of galaxies, something like 100,000 galaxies, all connected to one another gravitationally and currently moving in a relatively similar fashion. They're not moving in the same direction, but they are sort of connected. But in the last few years, scientists have also discovered that this is only temporarily. As a matter of fact, within the next few billion years, the Laniakea cluster, because of the interaction from the dark energy, is actually going to fall apart and form smaller structures. But despite of this, it's still the biggest structure where we're currently located, made out of several superclusters you see in this particular map right here. And we generally know that things here are always in motion and are always moving. But because of the scale of things, it's practically impossible to detect this in real time, which generally is how the universe works. Small things generally move really fast and generally live in their own time scale. Large, massive things move really slow and also have their own scale as well. Nevertheless, because of various observations in the last few decades, the scientists have been slowly making a kind of a map of everything around us, mostly focusing on the motion of various clusters in the night skies and trying to figure out where everything was sort of going. With several recent studies being able to create a three-dimensional image out of the 2D map that we currently have. With this recent study specifically focusing on various galactic clusters, around 10,000 of them as a matter of fact, and everything that's within about 350 million light years away from us. But here they really just focused on the motion and the evolution of various objects in the vicinity. They focused on several objects, but essentially here they just tracked the motion across the night skies in the last few billion years, but also trying to project it into the future. As a matter of fact, the simulation itself that you can find in the description below starts at roughly around 11.5 billion years ago when the universe was only 1.5 billion years old. With the simulation then showing us how all of this moved for about 11.5 billion years. But here they also introduced the idea of the dark energy, or essentially galaxies moving farther and farther away from one another, and also the idea of dark matter, and the idea of various galactic clusters that tend to chunk together. And so even though at first a lot of these galaxies were more or less equally distributed, over time because of the gravitational interactions, they tend to follow the regions of higher density and then essentially form larger structures this way. And that's how these clusters form things like filaments, and that's how essentially voids form, basically the space or the low density space between the galactic clusters. But more importantly, that's how our home Laniakea was formed. With this part right here being Laniakea itself. And by definition, this particular tremendously large structure is defined as a lot of galactic clusters moving towards some kind of a central point. In this case, we refer to this point as the Great Attractor. A mysterious structure with a mysterious name and mysterious origins behind it. And this Hubble image kind of shows us where this particular attractor is. And if we were to look at the more familiar map of the Milky Way, it's kind of somewhere right here. And by definition, this is the core of Laniakea supercluster. But it's also extremely difficult to study because of its location, where, as you can see from this image, it's kind of hidden by the galactic plane of our own galaxy. It's essentially in what we sometimes refer to as the zone of avoidance, the tremendously thick layer of gas that's formed by the galaxy itself that kind of blocks a lot of the things behind the galaxy. And because the attractor is somewhere right here, it becomes extremely difficult to figure out what exactly it is. Nevertheless, it seems to be there based on the observations of all of the nearby clusters sort of headed that way. With this simulation of a Laniakea supercluster showing us how the motion sort of looks like. So you can kind of see that a lot of the arrows are sort of headed this way somewhere. And that sort of represents this unusual gravitational attraction that many clusters headed toward. Nobody obviously knows what it is, but it's very massive. Its mass is several million times higher than the mass of our own galaxy, and it seems to have an effect that stretches across millions of light years. A lot of the galaxies and clusters moving toward this point are showing redshift changes of nearly 700 kilometers per second, which means that this is a very powerful, extremely massive whatever. We don't really know what it is. It's probably not just a single structure, it's probably a concentration of mass, possibly even a really large concentration of mass, but either way, it's currently unknown exactly what it represents and exactly what it's made out of. Which is why it's normally just referred to as a gravitational anomaly or the Great Attractor anomaly, with the supercluster known as Vela supercluster very likely being the point closest to the center of this anomaly. But on top of this, the scientists in the study decided to investigate several other structures. For example, they also took a look at an extremely large structure, the structure that you can kind of see right here, sometimes referred to as the Great Wall, one of the larger superstructures in the universe. In this case, once again showing where things are moving and how a lot of the mass seems to be congregating toward a central point, in this particular case near the Coma cluster. The cluster that became famous because of the unusual observations of tremendously large amounts of dark matter on the inside, and just overall being one of the largest galactic structures in the vicinity. This beautiful NASA image sort of shows us what all of this looks like. And then they also focused on the other structure, sometimes referred to as the Perseus-Pisces filament, the part that you see right there on the right next to the Laniakea supercluster. And this here is one of the largest known structures in the entire universe. At a distance of 250 million light years away from us, this is once again a structure made out of galactic clusters. But in this case, it also seems to be extremely dense and highly concentrated in many different types of galaxies, with many of these clusters and many of these galaxies once again moving towards some sort of a central region. But because on the grander scale of things, the dark energy is still the dominant force here, once we start looking into the motion of the galaxies into the future, things start to move apart a lot more, and a lot of the previous structures become non-existent. So things like Laniakea are going to fall apart, forming much smaller, much more compact structures, which will then fall apart later on as well. Here's one of the examples of one of the smaller galactic structures that's most likely going to form in the next few 10 billion years. Here's another really good example from the Great Attractor region, or specifically where we think it's located. In this case, it kind of shows us where everything is going to be moving for the next 10 or so billion years, and how everything is going to evolve over time. So this is essentially 10 billion years from now. And even though it doesn't look that different, in this case, a lot of the clusters do become a lot more concentrated, and a lot of the things that were not as gravitationally connected before eventually fly away from us and, because of the expansion of the universe, become invisible over time. And so overall, this is a pretty interesting study and extremely interesting simulations, sort of showing us how many of these grandiose structures are going to be evolving over time. But I guess more importantly, possibly answering some of the questions in regards to what's happening with a lot of these gravitational anomalies. Now, we still don't really have exact answers, but because we are now able to form much better 3D maps and understand where things are headed, it becomes slightly easier to figure out exactly what's forming all of this and where everything is headed, or where it's going to be headed in the next few billions of years. But once again, because these things are so tremendously large in terms of size, none of this will really ever affect anything here on planet Earth. Even if all of these structures start colliding and things become just one big chunk of galaxies, here we're probably not even going to notice, even if we're still alive. Which is, I guess, a pretty good reminder that we're just a tiny speck of dust when it comes to the universe at large. But honestly, I'm always fascinated by studies like this, and I'm always excited to talk about some of the new discoveries. When the scientists originally proposed the idea of Laniakea, it was already pretty groundbreaking. The video once again in the description. But now we have so many more details, including the actual pathways that we think these clusters are taking, that help us understand how this will evolve and how it's going to transform, potentially changing everything we see around us and obviously changing the night skies as well. Hello wonderful person, this is Anton, and this right here is Smiley. This is a gravitational lens formed through the interaction of different galaxies and different galactic clusters, creating this beautiful image. And as you might already know, a lot of different beautiful images out there, especially the ones discovered in the last few decades, have been a result of some sort of a gravitational lens or gravitational lensing effects. And although today scientists generally can explain pretty much most of the gravitational lenses and the effects that they form through the analysis using a lot of Einsteinian theories, sometimes the scientists do discover something that's somewhat difficult to explain. And today we're actually going to be talking about one such object that was only explained very recently, but was known to us for almost a decade. The unusual object you see right here, known as the Hamilton's object. The strange galactic object that was discovered completely by accident when the scientists were looking at and measuring various distant quasars located in a somewhat similar region. And so in this video we're going to be discussing the explanation for this unusual double galaxy, as you can see it right here, and the implications this discovery has on our understanding of what the universe is actually made out of. But first of all, well, I guess it's important to sort of understand that when we're actually looking at different distant galaxies and when we're looking across the universe, we're going to be seeing a lot of different mirroring effects and a lot of different distortion that's generally formed through the interaction of different matter and light that passes close to it. But these particular effects are not always apparent to us. In some cases they are very obvious, like for example when we're looking at a very distant quasar and suddenly discover that it forms something like this. This is known as the Einstein's cross. In this case we're pretty certain that what we're looking at is indeed a gravitational lensing effect. Something very similar is happening in this galaxy here as well. And in some other cases we usually see these effects as something really massive passes in front of a distant star, making the star slightly brighter and also forming unusual effects such as mirroring effects that sometimes last anywhere from a few hours to possibly a few days. But obviously, not all of them are so apparent. Not everything is going to produce something similar to this. In some cases, these effects are not as obvious and only become apparent once you actually start looking for them. In other cases, they produce something that's extremely difficult to explain, like this beautiful stretched galaxy you see right here. And in other cases, they produce something that doesn't even look like a galaxy, and usually takes anywhere from a few months to possibly even a few years to finally figure out what we're actually looking at. And so it's sort of important to realize that everything around us kind of acts like this unusual mirror maze that you sometimes find in certain theme parks or certain amusement parks. So a lot of things we're looking at are either not necessarily there or are producing light that's entirely different from what we get to see here on planet Earth. And in some cases, many of these things might not even exist. A lot of the light that's received on the planet could be a result of essentially a visual illusion. So sort of like the smiley you see right here. But despite all of these optical illusions, they actually provide an extremely important tool for the scientists that allows the scientists to study objects that would be otherwise invisible to us, while also helping us figure out a lot of features of the universe itself. For example, by comparing different mirror images coming from the same quasar, we can typically start figuring out how the space between the galaxies behave, and even how fast the universe itself is expanding. But more importantly, a lot of modern techniques also allow us to reconstruct these galaxies, helping us visualize what a lot of these ancient galaxies might have looked like, and thus understand what happened in the beginning of the universe and how these galaxies were different from the galaxies today. And in the last few decades, the scientists have seen pretty much everything. They've seen different galaxies forming unusual shapes, they've even seen different distant supernovae, and some other unusual objects that were only visible through the gravitational lensing effects. And most importantly, time and time again, these scientists, after every gravitational lens, were able to explain everything they're observing to extreme detail. But that's until relatively recent discovery of this unusual object. The object that's referred to as the Hamilton's object. And what the scientists were seeing here was very difficult to explain. It seemed to be some sort of a double galaxy, with the other very similar object located not so far from it in the region right here. And so what exactly was happening here, and how exactly was any of this formed? When the scientists originally discovered this, they really had no idea. At first they thought maybe they were looking at some kind of an unusual collision between two galaxies. But what made this collision really strange and very difficult to explain is the fact that the galaxies looked almost identical, and they also formed a shape that we've never seen before. And also the appearance of that third galaxy that looked very similar to the other two made no sense either. The other mystery here was that, okay, if this is a gravitational lens, which was one of the explanations, what is making all of this lens? What's making the gravitational lens happen? Normally you would have either some sort of a galactic cluster or some sort of a galaxy in front of all of this. But nothing here stood out as a potential gravitational lens. And so after years and years of speculating, analyzing, talking to different people at different conferences, and trying time and time again to explain this, the scientists finally figured it out. And it looks like this is one of the rarest occurrences of what seems to be a gravitational lens, but in this case not actually formed by any galaxy. As a matter of fact, this once again is one of the most definitive proofs for the existence of the unusual dark matter. This very strange, very rare phenomenon seems to have occurred simply because the galaxy passed right in front of a large ripple of a fabric of space-time, and this ripple was very likely formed by huge dense amounts of dark matter. Whatever it is, we still have no idea what it is and what it's made out of, but it just seems to exist, and this particular discovery seems to prove it once again. And so let's talk about some of the details here. Now first of all, the paper in the description below proves without a doubt that all three objects are basically the same galaxy. You can see them in A, B, and C. And so this definitively proves that this is a gravitational lensing effect. In this case, the scientists established that this is a galaxy that's about 11 billion light years away from us. But what is producing the lensing effect, and what's causing the galaxy to look the way it is? Well, it turns out that this location does have a galactic cluster located in the region that we're looking at. It's about 7 billion light years away from us, with the approximate center of the galactic cluster being somewhere right here. The cluster itself was only discovered later on and was not actually present in a lot of different surveys. And so in this case, it became quite apparent that it was really the galactic cluster and the mass in the cluster that was producing these effects. But the question here is, why did it not look like a typical Einstein's cross? Or any of the other formations we've seen from some of the previous gravitational lensing formations, such as once again the smiley right here? Well, it's because of the effect that's being formed here, the unusual rare phenomenon formed by the actual ripple itself. The comparison scientists use here is essentially the type of reflections you see on the seafloor right here that are in reality formed by the ripples formed on the surface of the water. A lot of these distortions and mirror effects are produced by the waves and the ripples on the surface, and something extremely similar happened right here as well. As the galactic light from this galaxy passed through the ripple of space-time formed by the dark matter, it ended up bending the light, producing not a typical Einstein's ring, but a much more unusual formation of several mirrored images that at least for now we're going to be referring to as the Hamilton's object. And so in this case, the ripples on the surface act as partial lenses. They end up focusing the light in different ways, producing various patterns that we see on the bottom of the seafloor. And so now imagine this, but in outer space, and instead of water, imagine a lot of dark matter moving around, shuffling around, and producing a lot of these wavy effects. And you basically get this as a result. But because of the rarity of this unusual phenomenon, at least for now, this is probably the best known example. Although there's a very high chance that we've seen a lot of these in the past, we just had no idea what we're looking at. Depending on how often this happens, it's quite likely that some of the galaxies that might appear the same could actually be the same galaxy that's just basically mirrored by another very massive space-time ripple. And so this would be a really interesting phenomenon to investigate and to find out more about, although at least at the moment it would be really difficult to find out what exactly is an actual galaxy and what is just a mirror image. But through this analysis, the scientists also discovered a lot of other things. For example, we know now that this is a typical spiral disk galaxy that seems to have a lot of clumpy star formation. In other words, stars form in extremely dense regions. The scientists have also established that the distribution of dark matter in this particular region seems to be, for the most part, more or less smooth, which at least in theory could one day help us identify what exactly is causing these effects and basically answer the question of what exactly is this dark matter. But because in this case it seems to suggest that the actual dark matter clumps are somewhat small in size, it also implies that the particle has to be very massive if it is a particle. But if it's formed by something else that's not a particle, well, in this case it needs to be explained in some other way. Although trying to explain this without the existence of dark matter would be, at the moment, pretty much impossible. Whatever is happening in this particular region is definitely caused by something invisible and something extremely massive. But something that doesn't seem to be a black hole, because we would probably see the effects from this as well. And so even though the mystery of the Hamilton's object, at least for now, has been solved, there are still a lot of unanswered questions and a lot of things we'll be talking about in some of the future videos. Hello wonderful person, this is Anton, and today we're going to be talking about this right here, which happens to be a tremendously huge cloud of gas located in a relatively distant part of the universe. A cloud of what seems to be extremely hot and very massive gas, something that the scientists have never seen before, and something that the scientists are currently referring to as the intra-cluster medium clumping. And interestingly enough, in terms of size, it's even larger than the Milky Way galaxy, with the total mass of about 10 billion masses of the Sun, which is really massive. It's sort of comparable to some of the smaller galaxies orbiting around the Milky Way. And so I wanted to talk about this because this is a very strange discovery and it's never really been seen before. But first of all, where exactly is this located? Well, all of this is part of this relatively large and really well-known cluster known as the Leo cluster. Here's what the actual image of this cluster looks like, and it's also sometimes referred to as the Abell 1367. It's about 330 million light years away from us, and there are roughly around 70 major galaxies in this cluster, with the galaxy known as NGC 3842 that you see right here being essentially the brightest member of the entire cluster, which, by the way, we can jump to right here in Space Engine, and it's located somewhere in this region right there. Now, interestingly, this cluster is right next to the famous Coma cluster. Coma cluster, which you can see right here, is much larger and much more massive, but it also seems to be much older. But they are next to each other, and together they form what's known as the Coma supercluster, essentially this really large structure that also happens to be a part of a much larger structure, the structure you see right here known as CFA2 Great Wall. And to try to imagine where all of this is located compared to, I guess, us, with us being right there in the middle, the Coma supercluster along with the Leo cluster are essentially in this region. And what makes Leo cluster somewhat unusual is that most galaxies here are spiral galaxies. They're actually much younger than comparable galaxies in the universe. You can sort of make out their shapes here and there, and for the most part they do seem to be some of the younger galaxies we've examined so far. And this galaxy right here that I previously mentioned also happens to have one of the biggest black holes in the center, roughly around 10 billion masses of the Sun. But overall, this region is also extremely active and there's a lot of stuff going on. There are a lot of collisions, there are a lot of nearby passes between galaxies, or at least there have been in the past. And as a result, these galaxies do not really form as many stars as some of the other galaxies in the vicinity. On top of this, because of all of these interactions and because of all of these collisions, some of the gas here occasionally gets stripped from the galaxies, and to some extent occasionally ends up producing something that you're about to see in this galaxy. This is a simulation produced by NASA and by ESA. So this is caused by ram pressure when the galaxy flies through a lot of different hot gas that's already in the intergalactic space. And it creates these very unusual patterns that you see right here. But when there's a lot of activity and when there's a lot of ram pressure involved, this whole gas right here can actually escape a galaxy and, to some extent, permanently escape from a galaxy and create its own structure by itself. Now this has been sort of predicted and theorized, and it's also been seen to some smaller extent, but the scientists have never seen something so large as this particular cloud that was discovered relatively recently. So this right here is a few 100,000 light years across. This is bigger than the Milky Way galaxy. And the images from this gas cloud were received by several different telescopes, including the XMM, which looks at things in X-ray, and also some of the other telescopes that looked at this in the optical light. Which of course implies that this is definitely a structure that's there. It's a structure that's extremely large and extremely massive, with the temperatures of gas here being about 10,000 Kelvin up to about 10 million Kelvin in some of the more extreme regions of this cloud. But what's particularly unusual about this discovery is the location. The cloud itself seems to be really far away from any major galaxy and seems to be in the no galactic zone. Or basically, even if it was formed this way, it's not clear what galaxy it came from or what exactly was responsible for its formation. Or essentially what I'm trying to say here is we don't really know how this was formed. Nobody has a good explanation for where it came from or what exactly created this. Which also of course makes this one of the more unique features and more unique structures discovered in the last few years. Now it's of course assumed that it came from a large galaxy and really massive galaxy nearby. It's just not really clear which one and exactly what caused the stripping effect to occur as well. Nevertheless, the analysis of the cloud itself, including the temperature of the gas in it, does suggest that it probably came from some sort of an ancient galaxy somewhere. Maybe this galaxy no longer exists because it was basically destroyed or absorbed by something else. Maybe it was created a long time ago. Either way, it's very unusual that this cloud still exists, and this is actually the biggest mystery about it. How is it that it's still there? For some unexplained reason, the cloud seems to maintain its own shape, and most likely has done so for millions if not billions of years. And so the scientists believe that in order for such an object, such a massive, huge object, not to fall apart and not to be absorbed by something else, there has to be something else involved here. And currently they believe that it's very likely extremely powerful magnetic fields. The fields that are very likely just sort of holding the object together and preventing things from falling apart too quickly, and possibly even bringing more things into the cloud itself. Which of course makes this one of the most eerie and most unusual objects discovered. Because the way it looks right now is as if someone took a galaxy, stripped all of the stars and obviously planets out of it, then most likely also removing black holes and neutron stars and so on, then just left gas kind of moving around without anything really keeping it together, with the magnetic field then sort of doing the job of keeping the object whole. Now that's a very unusual, very interesting formation. Although there are actually signs of some stars being present and being formed as well, simply based on the emissions, specifically various hydrogen emissions, that the scientists were able to detect. And so one way of imagining what this probably all looks like on the inside is maybe by examining one of the nebula we have inside our own galaxy, such as of course the famous Carina Nebula that you see right here. So these nebula are mostly gas, but there are occasional stars on the inside as well, naturally formed by the gas itself. But there's also quite a lot of magnetic fields and magnetic lines here, and quite a lot of magnetic interaction. So imagine this, but way bigger, like thousands and thousands of times bigger. And so that sort of is what the scientists just discovered, although also probably not very dense, not as dense as you see here. Nevertheless, a really interesting discovery and a super cool cloud somewhere out there in a very famous cluster. Although unfortunately for now, that's kind of all we know about this new discovery. I'm sure there are going to be more studies and more follow-ups describing this in more detail. For now, we don't really know much else. Well, on that note, thank you for watching, subscribe if you still haven't, share this with someone who loves to learn about space and sciences, and maybe come back tomorrow to learn something else. Maybe support this channel on Patreon by joining the channel membership, or by buying the Wonderful Person t-shirt you can find in the description. Either way, stay wonderful, I'll see you tomorrow, and as always, bye bye.